Welcome to the official developer training course for the Blue Prism AD01 certification. We will examine the core competencies required to succeed in the exam and build production-ready automation solutions. This is an unofficial, independently produced training course. It is not affiliated with, endorsed by, or connected to Blue Prism Limited in any way. All trademarks belong to their respective owners. This course is designed to transition you from a novice to a certified Blue Prism professional. You will gain the technical skills necessary to architect scalable, resilient, and reusable automation workflows. By focusing on best practices, we ensure that you are not just learning to pass an exam, but to implement industry-standard robotic process automation. We have structured this curriculum to mirror the real-world demands faced by senior RPA developers. Choosing this path provides a solid foundation for mastering both the theoretical constructs and the practical implementation of intelligent automation. The AD01 exam evaluates your knowledge of the Blue Prism platform, focusing on technical proficiency, architectural understanding, and operational integrity. You will be tested on your ability to navigate the process and object studios, handle exceptions, manage work queues, and deploy secure, maintainable packages. The exam requires a deep understanding of standard conventions, as Blue Prism values consistency and modularity above simple functional code. Success hinges on your ability to interpret requirements and translate them into robust, efficient, and auditable digital processes. Achieving this certification marks you as a qualified developer capable of managing enterprise-scale digital workforces. We will begin by establishing a baseline understanding of the Blue Prism environment, starting with the core architecture and interface navigation. From there, we move into the structural nuances of object and process design, which remain the engine of any successful automation. You will learn to manipulate data, manage exceptions, and configure enterprise-level work queues to handle high-volume transactions reliably. The latter modules will focus on lifecycle governance, deployment best practices, and security, ensuring your processes remain secure and manageable within complex IT infrastructures. Through this systematic approach, we will thoroughly cover every domain required to earn your certification. As we progress through the material, you will find that our focus remains strictly on technical accuracy. We will avoid shortcuts that might lead to brittle code, instead advocating for the rigorous patterns that keep production environments stable. Developing for Blue Prism is effectively an exercise in high-discipline engineering, where maintainability is the primary metric of success. If you apply the methodical approach outlined in these sessions, you will discover that passing the exam becomes a tangible and highly achievable outcome. We will spend time ensuring that your grasp of the fundamental concepts is beyond reproach before layering on advanced configuration techniques. I look forward to guiding you through this journey. See you in the next lesson. Welcome back. In this chapter, we will focus on mastering the Process Studio environment as the primary canvas for designing your automation workflows. Process Studio is the central workspace within Blue Prism, designed to mirror the actual flow of a business process through visual diagramming. When you open an existing process or create a new one, you are presented with a blank canvas governed by a set of nodes and links that define the execution path. Understanding this interface is not merely about knowing where the buttons are, but about internalizing how the engine traverses the diagram from the start stage to the end stage. At its most fundamental level, the workspace is an object-oriented modeling surface where you drag and drop predefined stages, such as actions, decisions, and calculations, onto the canvas. Crucially, the order of these stages matters significantly because the Blue Prism logic engine executes steps linearly unless redirected by branching logic or subpage calls. You should treat this canvas as a finite space where clarity is paramount. Overcrowding a single page makes troubleshooting difficult and version control a nightmare. Therefore, managing your diagram boundaries involves a disciplined approach to spacing your components, ensuring that every link is visible and every stage is properly labeled for future maintainability. Organization is one of the most critical aspects of professional robotic process automation development, often separating novice implementations from enterprise-grade solutions. If you find your diagram spanning hundreds of pixels in a single view, you are likely failing to utilize subpages effectively. Subpages allow you to abstract complex segments of your logic into modular, distinct groupings that can be called repeatedly. This promotes high reusability and significantly improves readability, as it allows a developer to grasp the high-level intent of a process without being buried in fine-grained implementation details. When designing these flows, think of each subpage as a self-contained function that should ideally have a single responsibility. By keeping your logic modular, you also make the process more resilient to change, as modifying a specific piece of functionality only requires adjustments within the relevant subpage rather than surgically removing nodes from a tangled web of links. Always name your pages clearly, as the navigation bar on the left becomes your table of contents when you inevitably revisit the process to update it months later. Configuring stage properties is an iterative exercise that requires precision and consistent naming conventions. Each stage, whether it is a simple action or a complex collection operation, carries its own set of internal properties that define what the robot actually does at runtime. When you open the properties dialog for a stage, you are defining the variables, targets, or inputs that the process depends on, and these must be configured with rigor to avoid runtime failures. To validate your design, Blue Prism provides a suite of execution controls that allow you to step through your diagram one stage at a time or run the entire flow from beginning to end. This is where the standard toolbar becomes your most trusted companion. The ability to pause execution, inspect data items, and evaluate local variables is essential for debugging. If you observe the execution in real time, you can often spot logical dead ends or incorrect branching paths before they ever reach a production environment. Make it a habit to use the stepping functionality during initial development, as it forces you to observe how data enters and leaves each stage, helping you refine your logic before scaling the process. See you in the next lecture. Welcome back. In this lecture, we will explore the foundational architecture of Object Studio and learn how the application modeler facilitates interaction with external software systems. In Blue Prism, the distinction between Process Studio and Object Studio is as vital as separating concerns in traditional software engineering. Process Studio acts as the orchestrator of your business logic, dictating the flow and decision-making high-level steps, while Object Studio serves as the interface layer that manages direct interaction with external target applications. Think of Process Studio as the brain that manages the what and why of a business requirement, while Object Studio acts as the hands, performing the exact mouse clicks and keystrokes required to manipulate a specific interface. By strictly segregating these two concerns, you ensure that any change in the user interface or application structure is confined to the business object layer, leaving your process logic completely untouched and stable. This is a design pattern that pays dividends when your target application inevitably receives a version update or a UI overhaul. To bridge the gap between Blue Prism and an external system, the application modeler serves as the essential gateway for discovery and element identification. When you initiate the wizard, you are primarily tasked with defining the technology stack required for the connection, such as Windows, Java, mainframe, or browser-based systems. Choosing the correct technology is not merely a formality, but a critical configuration step that determines the underlying spying mechanism Blue Prism utilizes to interact with the runtime environment. For instance, selecting an active accessibility or UI automation mode for a Windows application provides a structured way to expose the document object model to your automation. Once the application type is specified, the modeler allows you to navigate the hierarchical structure of the target interface to identify and isolate specific controls, such as text fields, buttons, or checkboxes. When we speak of business objects within Object Studio, we must emphasize the concept of reusability to avoid the trap of redundant code. A well-designed business object should encapsulate a logical set of actions, like logging in, searching for a record, or extracting data, that can be called multiple times across entirely different processes. By building these objects with a modular mindset, you essentially create a library of components that act as a standardized interface for your entire automation ecosystem. If you find yourself duplicating logic in different objects, you are likely missing an opportunity to abstract that functionality into a single, maintainable action. This approach not only streamlines your development effort, but also ensures that when a bug is identified in an interaction, you only have one location to update. which propagates the fix throughout your entire production environment instantly. Understanding the execution context is another fundamental pillar for any developer seeking to master the Blue Prism runtime. When a process runs, every action performed inside an Object Studio object occurs in the context of the business object, while the flow resides in the process. It is tempting for new developers to place business decisions inside Object Studio to simplify their process flow, but this is a significant architectural error that violates the principle of separation of concerns. Instead, let your business objects remain dumb regarding the end-to-end process requirements. They should perform their single, focused task and return status or error information back to the calling process. By maintaining this clean interface, you ensure that your business objects remain as generic and reusable as possible, which is the hallmark of a senior-level RPA developer. Effective modeling requires you to treat your application map as a source-controlled codebase that demands clarity and rigorous naming conventions. Within the application modeler, the hierarchy you establish should mimic the logical structure of the application itself, making elements easy to locate for other developers on your team. Always opt for attributes that are stable over time, such as unique IDs or permanent internal names, rather than volatile attributes like coordinates or unreliable labels that change frequently. If you design your objects with the expectation that they might be used by a process you haven't even conceived of yet, you will naturally move toward a more decoupled and robust design. Remember that the ultimate goal is not just to get the automation working for today, but to build an ecosystem of objects that can support a scaling digital workforce for years to come. See you in the next lecture. Welcome to this chapter where we will explore the control room interface to master operational management, infrastructure oversight, and digital worker deployment. This session will ground you in the practical realities of managing live environments, ensuring you can confidently deploy and monitor your automations. Navigating the control room is essentially where the rubber meets the road in a Blue Prism implementation. While Process Studio is our workbench for design, the control room acts as the cockpit from which we oversee the life cycle of our digital workers. We start by interacting with the tree view on the left, which organizes our processes and objects, and the resource list that displays the current state of our connected runtime resources. When a resource is online, it is ready to receive instructions, and your primary responsibility as a developer is to ensure that these resources are correctly grouped into pools. Resource pools are a logical abstraction that allows you to distribute workload across multiple machines, preventing bottlenecks that occur when a single, high-demand process is tied to only one physical robot. Monitoring the environment involves a continuous loop of checking session status and resource health. When you trigger a process, it transitions from a pending state to running, provided a compatible resource is available within the requested pool. You must observe the session log frequently, as it serves as the ultimate source of truth when a process deviates from its expected path. Blue Prism records every stage transition, input, and output within these logs, which are accessible through the session viewer. If a session fails or hangs, the log allows you to backtrack through the execution history to identify exactly which stage caused the obstruction. Pay close attention to exceptions appearing in these logs, as they often hint at environmental instability rather than logical flaws in your process flow. Effective resource management implies a deep understanding of session allocation strategies. By right-clicking on a resource or a pool, you gain the ability to launch specific processes, effectively overriding the schedule if an urgent business requirement arises. This manual intervention is occasionally necessary, but the goal of a robust automation architecture is to rely on automated schedules defined in the control room. These schedules dictate when processes start and where they run, enabling a hands-off approach to enterprise operations. You should organize your processes into logical folders within the interface to maintain clarity as your portfolio of automations grows into the dozens or hundreds. Keeping this hierarchy clean is not merely a housekeeping task. It is critical for preventing misconfiguration errors during deployment. Troubleshooting in the production environment requires moving beyond mere surface observation. When a session terminates unexpectedly, you need to check the status column in the control room, which identifies whether the process finished successfully or reached a terminal state due to an unhandled exception. Identifying the difference between a terminated session and a successfully completed one is the first step in root cause analysis. Always verify the interaction between the runtime resource's identity and the permissions set in the system manager, as many operational failures are caused by credential mismatches. Developing a methodical approach to checking these logs ensures that you remain proactive rather than reactive when managing your digital workforce. I will see you in the next lecture. Welcome back. In this lecture, we are going to explore the release manager and how it facilitates the movement of automated solutions across different environments. When we transition a solution from a development environment to a production environment, we rarely deal with a single file. An enterprise-grade Blue Prism solution consists of a complex web of processes, business objects, work queues, and environment variables. The release manager is the architectural component designed specifically to package these disparate assets into a single, deployable entity. By organizing components into a release package, we ensure that every dependency is accounted for, preventing the common missing component errors that arise during manual migrations. This is fundamentally an exercise in state management, where we encapsulate the entire logical definition of our automation to ensure it remains consistent across the infrastructure. Creating an effective release package requires a methodical approach to component inclusion. You begin by creating a new release within the manager and defining which items, such as specific business objects or processes, should be included. It is crucial to remember that Blue Prism automatically identifies dependencies, but you must oversee this process to ensure that only the correct versions are shipped. For instance, if a process relies on a specific credential or an environment variable, these must be explicitly bundled into the package definition. Failing to bundle a dependent business object will result in a failed import, as the target environment will lack the necessary instructions for the runtime resources to execute the logic. Once your components are identified and verified, the next phase involves generating the BP lease file. This file acts as a manifest that tells the target environment exactly what to expect and how to reconfigure itself upon arrival. When you import this file into a staging or production instance, the release manager performs an integrity check. It compares the incoming versions against existing items in the target database. If a conflict arises, such as trying to override a business object that is currently in use or has been modified locally, the system provides warnings to prevent data loss or service disruption. This validation step is the heartbeat of a secure and professional deployment pipeline. Effective lifecycle management goes beyond the technical act of importing files. It requires a disciplined adherence to versioning strategies. In a mature environment, you should never treat your releases as disposable or anonymous artifacts. Each release package should be tracked according to its purpose, whether it is a hotfix, a feature upgrade, or a new process deployment. By maintaining a clean audit trail within the release manager, you provide visibility to system administrators regarding exactly what code is running on which resource at any given time. This traceability is essential when troubleshooting, as it allows you to correlate current production behavior with a known, versioned state of your business objects. Managing dependencies is perhaps the most intellectually demanding aspect of release orchestration. Because Blue Prism objects and processes are often interconnected, a change in one object can have a ripple effect across multiple automations. When you bundle a package, you are essentially defining a snapshot of the current architectural state. If your deployment pipeline involves multiple environments, you must ensure that shared components, like common utility objects, are kept in sync. This prevents version skew, where one part of your system expects an updated method that does not yet exist in the target database, leading to runtime exceptions that could have been avoided through proper dependency analysis. Secure deployment is the final piece of the puzzle, particularly when handling sensitive credentials or environment-specific data. Using environment variables allows you to decouple a process from its environment, making it portable. During the release process, the target environment can be configured to map these variables to specific production values without altering the underlying code. The release manager respects these boundaries, ensuring that you do not inadvertently export sensitive hard-coded data alongside your logic. By adhering to these standard practices, you create a robust, repeatable mechanism for moving code that is both resilient to change and prepared for the rigors of production operations. I will see you in the next lecture. Welcome back to the course, where we turn our attention toward the architectural cornerstones required for building enterprise-grade RPA solutions. In this chapter, we explore the architectural principles necessary for designing scalable and resilient automated processes within the Blue Prism ecosystem. We will focus on strategies to optimize resource utilization, ensure zero downtime execution models, and maintain long-term system stability. When we approach the design of a Blue Prism solution, we must shift our mindset from thinking about a single process to considering the long-term lifecycle of an enterprise service. A common pitfall for developers is to build tightly coupled logic that functions well in a development environment but fails under the strain of high-volume, production-grade workloads. To achieve scalability, we must decouple our data ingestion from the actual transactional processing logic to ensure that bottlenecks at the intake stage do not cause the entire automation pipeline to stall. By leveraging work queues as the primary buffer between these processes, we enable a horizontal scaling strategy where multiple runtime resources can pull and process work items simultaneously. This decoupling is not merely a convenience, but a fundamental requirement for environments where transaction spikes are frequent and unpredictable. If your data layer is tightly integrated with your front-end interactions, any slowdown in the external application latency will result in an immediate performance degradation for the entire process. Therefore, we design our solutions to treat the execution layer and the data management layer as distinct, interchangeable entities that communicate through standardized interfaces. Resilience, much like scalability, is an architectural choice that we incorporate long before we write the first line of code or map the first application element. An enterprise-grade robot should be capable of self-healing, recovering from transient application glitches, and gracefully handing off control when a permanent failure is detected. This necessitates a rigid adherence to standardized templates that govern how we handle errors, log operational data, and manage the state of active sessions. By utilizing consistent naming conventions and modular structural guidelines, we reduce the cognitive load on the development team and make it trivial to perform maintenance on legacy processes. Furthermore, consider the impact of resource utilization on your broader Blue Prism infrastructure. A process that consumes excessive memory or holds GUI locks longer than necessary is essentially stealing throughput from its fellow processes running on the same runtime resource pool. We prioritize efficient resource consumption by minimizing unnecessary application interactions and ensuring that each action taken by the software object is both intentional and essential to the completion of the business task. To guarantee maintainability, we must treat our Blue Prism objects and subpages as pure, reusable components that encapsulate specific application functions without leaking business logic into the Object Studio layer. When we observe the way experienced architects handle dependencies, we notice a clear pattern of abstraction that keeps the core process flow clean and readable. This separation of concerns allows us to update underlying application interfaces without breaking the high-level workflows that orchestrate the business logic. We must also consider the deployment lifecycle, as an enterprise solution requires automated, version release cycles that minimize the risk of human error during production updates. By adopting a mindset centered on zero downtime deployment, we ensure that while one version of a process is finishing its final queued items, a new version is prepared to seamlessly take over the influx of new work. This architecture relies heavily on the environment-specific configurations held within Blue Prism, keeping our hard-coded values to an absolute minimum, or, ideally, eliminating them entirely in favor of environment variables. When every component is designed as a standalone, modular, and configurable unit, the result is an ecosystem that can grow alongside the business rather than one that eventually calcifies under its own complexity. See you in the next lecture. Welcome back, and let us focus on how to build scalable automation ecosystems through rigorous standardization and reusability. When we approach enterprise-scale robotic process automation, the temptation to build quick, tactical solutions often leads to technical debt that slows down the entire department. Instead of viewing each process as a unique, isolated silo, we must adopt an engineering mindset that prioritizes the creation of centralized, reusable assets. By abstracting common application actions, such as login sequences, data validation routines, or standardized navigation patterns, into discrete, single-purpose business objects. We move from writing procedural scripts to building a robust component library. This shift is not merely about aesthetics. It is a fundamental architectural requirement for any organization scaling beyond a handful of digital workers. When you decompose a large process into these smaller, high-cohesion units, you gain the ability to test, update, and deploy specific functionalities without risking the stability of the parent process. This modularity ensures that if an underlying application interface changes, you only need to modify one point of failure rather than updating dozens of disparate processes across your entire production environment. Standardization is the bedrock upon which reliable automation is built, yet it is often the most neglected aspect of development practice. In Blue Prism, this is realized by enforcing strict coding standards, which include naming conventions for stages, consistent organizational patterns for subpages, and predictable data handling practices. Imagine a scenario where every developer on your team uses different approaches for error handling or data logging. The resulting system becomes a nightmare to audit and support. By implementing a standardized template for every business object, you ensure that anyone stepping into the code can immediately grasp the flow, the interfaces, and the state management logic. A essential component of this methodology is the use of peer-review checklists that enforce these design patterns before any code is promoted to the release pipe. These checklists should mandate that every public action in an object clearly defines its input and output parameters, as well as the explicit preconditions required for successful execution. Documenting these interfaces is not a bureaucratic exercise, but a vital communication tool that bridges the gap between different development teams. When another developer tries to consume a business object you created, they should be able to understand exactly how to interact with it just by inspecting its metadata and configuration without needing to dig into the internal implementation details. This encapsulation is a core tenet of software engineering, and it applies just as strictly to RPA as it does to traditional application development. By documenting the purpose of each stage, the expected format of input data, and the nature of the data returned, you foster a culture of cross-team component sharing. This approach drastically minimizes redundant development efforts, as common tasks are solved once and then leveraged repeatedly across the enterprise footprint. As your library of standardized objects grows, your delivery velocity will naturally increase, allowing your team to focus on high-value business logic rather than recreating basic application interactions. See you in the next lecture. Welcome back. In this session, we will delve into the mechanics of constructing reusable business objects and the granular control required to expose their functionality effectively within Blue Prism. When we approach the development of a Blue Prism solution, the primary distinction between a process and an object lies in the abstraction of interaction. A business object should represent a specific, logical piece of software interaction, such as interfacing with a CRM or a legacy mainframe screen, rather than a sequence of business tasks. To build a robust object, you must first define clear boundaries within the application modeler. Encapsulation is key here. Every element you spy should be scoped to the specific window or container it belongs to, reducing the risk of global element collisions that often plague poorly maintained projects. By strictly defining the application interface, you ensure that any future UI changes in the target application only necessitate updates within the Object Studio, leaving your higher-level process flows completely untouched. This is the cornerstone of maintainability in professional robotics. Once your elements are mapped, you shift focus to the creation of specialized actions. An action should be atomic, meaning it performs one clear task from start to finish, such as login or get customer details. You must carefully configure your input and output arguments to act as a contract between the process studio and your object. By assigning clear data types and meaningful descriptions to these parameters, you provide a self-documenting interface for other developers. Before executing the main logic of an action, you should always implement preconditions to verify that the application is in an expected state. If your action requires a specific screen to be visible before it can interact with a control, a precondition check prevents early runtime failures and provides more actionable feedback during debugging. Managing object-level data items requires a disciplined approach to scope and memory. Unlike process-level data items that may persist throughout a long-running transaction, Object-level data must be carefully managed to avoid state leakage between action executions. You should ensure that any variables utilized for UI state tracking are initialized or reset effectively at the beginning or end of every action cycle. This is particularly critical when dealing with objects that remain open for long periods. Failing to reset internal flags can lead to insidious bugs where the object believes it is already logged in or currently focused on a specific screen when it is not. Always favor local action data items over global object data items whenever possible to minimize the potential for accidental state mutation between independent calls. To make your object useful, you must explicitly publish the actions that you intend for the Process Studio to consume. This acts as a gateway. It prevents the internal helper actions, those meant only for support, from cluttering the developer's view in Process Studio. Organize these actions into logical tabs within the Object Studio to keep the interface clean and navigable. Furthermore, your design must account for the full life cycle of the target application. This means implementing a robust cleanup action that handles unexpected application termination, triggers a graceful shutdown, and restores the interface to a neutral state. By treating your business objects as reliable, standalone components, you provide the necessary foundation for the highly resilient, scalable automation solutions that this certification requires. See you in the next lecture. Welcome back. In this chapter, we explore how Blue Prism interacts with various application interfaces through the application modeler's specific spying modes. To build stable automation objects, one must fundamentally understand how Blue Prism communicates with the underlying technology of the target software. When you attach to an application, you are essentially asking the platform to translate high-level commands into instructions that the operating system or browser understands. The Win32 mode remains the foundational choice for standard Windows desktop applications, as it interfaces directly with the Windows API to identify objects by handles or class names. This is typically the most robust and performant method, but it assumes the application exposes its internal structure in a standard way. If you find that objects are not being caught consistently, you might be dealing with an older legacy platform that requires the active accessibility mode. This mode pulls the accessibility layer designed for assistive technologies, which provides a fallback for applications that do not strictly adhere to standard Win32 architectural patterns. As we move toward modern web-based interfaces, the HTML spying mode becomes the primary tool in your repertoire. This mode interacts directly with the document object model, providing access to tag attributes, IDs, and CSS classes that define the web page structure. Since web frameworks are dynamic by nature, relying on HTML mode is far more reliable than relying on coordinates, provided the underlying markup remains consistent. When you encounter modern rich clients, such as those built with WPF or deep integration frameworks, the Microsoft User Interface Automation mode is often superior. This mode, commonly referred to as UIA, offers a sophisticated hierarchy that reflects the logical structure of complex UI elements, making it the preferred choice for complex software that does not fit neatly into traditional Win32 categories. Selecting the right mode is an exercise in weighing the responsiveness of the application against the potential for unstable element attributes. When direct interaction with the application's code is impossible, we fall back to the last resort, which is region mode, commonly known as surface automation. This method effectively treats the application window as a flat image, using coordinate offsets and visual anchors to find elements or perform mouse clicks. While this approach appears flexible because it works on any platform regardless of the technology stack, it is inherently the most brittle and least performance-friendly option. A slight change in screen resolution, window sizing, or theme settings can break the entire automation, forcing constant maintenance. Therefore, you should always treat region mode as an exception rather than a rule. You must exhaust all programmatically aware spying modes before deciding that the application interface provides no other way to reach the required controls. Understanding these distinctions allows you to architect solutions that will not break the moment a developer changes a UI layout or an application update pushes a new framework version. Always prioritize direct accessibility modes over visual ones to ensure your automations remain resilient across diverse environments. As you design your business objects, verify the framework used by your target application early in the analysis phase. If an element refuses to highlight, systematically switch through the available spying modes while keeping an eye on the attributes that appear in the element tree. A mastery of these modes is not just about capturing elements. It is about choosing the communication channel that keeps your automation logic isolated from superficial changes in the user interface. By aligning your technique with the application's native technology, you minimize technical debt and ensure long-term stability for your enterprise processes. See you in the next lecture. Welcome to this session on Mastering Application Modeler, where we will focus on handling dynamic elements and optimizing element identification. By the end of this discussion, you will understand exactly how to handle shifting interface attributes to build resilient Blue Prism objects. When we interact with complex enterprise applications, the interface is rarely as static as we might wish. Automation developers often find that perfectly captured elements stop working as soon as a window is resized, a tab is refreshed, or the underlying application updates its session parameters. The fundamental issue is that Blue Prism's spy modes by default might capture attributes that are inherently volatile. If your attribute list includes items like window titles that change with the document name, or process handles that increment upon every login, you are building a fragile foundation. The goal of advanced attribute tuning is to peel back these unstable layers, often found in the attribute configuration table, to isolate only the identifiers that remain constant throughout the application's lifecycle. Think of this process as defining a stable identity for an element despite its changing surroundings, much like identifying a person by their biometrics rather than their choice of clothing today. To gain control over these dynamic behaviors, you must become comfortable with the attribute table inside the application modeler. Once you've spied an element, you will see a list of attributes that Blue Prism uses for identification, and your first job is to critically evaluate which ones belong and which ones should be discarded. Volatile attributes, specifically those related to coordinates, window handles, or specific session IDs, are usually the culprits behind broken automations. If an attribute changes every time you restart the application, it creates a point of failure that will almost certainly lead to a runtime exception once the process moves to a production environment. By simply unchecking these volatile entries, you force the spy engine to rely on more robust attributes, such as internal names, IDs, or stable labels that do not fluctuate during the session. Reliability in RPA is built through subtraction. By removing the noise, you reveal the signal that allows the robot to find the target element consistently. Sometimes, simply unchecking attributes is not enough, because the application might cycle through several naming conventions or slightly variable strings. In these scenarios, changing the match type to a regular expression or utilizing wildcard characters becomes necessary for building flexible selectors. Using an asterisk allows you to represent 0 or more unknown characters, which is perfect for fields that might contain a dynamic transaction ID at the end of a static label. A question mark, on the other hand, deals with a single character variation, providing enough precision to be safe while allowing enough slack to satisfy the requirements of a dynamic environment. When you switch a match type to a regular expression, you gain access to a powerful syntax that can handle complex patterns, ensuring your robot remains productive even when the vendor updates their software labels. This design approach is far superior to reacting to every minor UI change, as it gracefully accommodates reasonable variance without requiring a developer to respy the element every time. Finally, we must address the challenge of duplicate elements, which often occurs in grids or repetitive forms where multiple inputs share the same underlying attributes. If the robot cannot distinguish between two identical text boxes, it will either throw an error or choose the wrong one, leading to data integrity issues. The match index property is the specific solution provided in the application modeler for this exact problem, allowing you to uniquely identify items based on their position in the object tree. By assigning a zero-based index value, you tell Blue Prism exactly which instance to target, effectively resolving ambiguity without compromising performance. Using the lowest possible index value is typically preferred, as it keeps your identification logic lean and minimizes the time the robot spends searching through the DOM or the screen object tree. When you combine this careful management of indexes with the selective use of attributes, you create a robust, production-ready object that respects the nuances of the host application. See you in the next lecture. Welcome back to our discussion on advanced automation techniques within Blue Prism. In this session, we will focus on designing highly resilient interaction models through the implementation of intelligent wait stages. When we construct automation in Object Studio, the primary challenge is synchronizing our execution speed with the inherent latency of the target application. Many developers fall into the habit of using static wait stages, which force the robot to pause for a hard-coded duration regardless of whether the application is ready. This approach is inherently brittle, as it either causes unnecessary delays or crashes when the application takes a fraction of a second longer than expected to process a request. Instead, we must favor dynamic wait stages that observe the state of the user interface in real time. By configuring wait stages to check for specific element properties, such as visibility or enabled status, we ensure the robot proceeds exactly at the moment the interface becomes interactive. This event-driven philosophy is the bedrock of non-procedural automation that can gracefully handle fluctuating server response times or unpredictable computer resource availability. A robust wait stage acts as a gatekeeper that validates the environment before attempting any further interaction, such as a read or write action. Within the wait stage configuration, we can define multiple conditional checks to account for various application states simultaneously. For example, rather than simply waiting for a button to exist, we might configure the stage to check if that button is both visible and enabled. Beyond these positive checks, we must also consider the utility of negative wait stages, which verify that an element has disappeared from the screen. This is particularly important when dealing with loading spinners, status bars, or modal dialogues that persist while a background process is active. By setting a wait condition to look for the absence of an element with a defined timeout, we effectively synchronize the workflow with the completion of a background task. When configuring these stages, the choice of timeout value requires careful consideration of both reliability and performance. A timeout that is too short may trigger an exception during a temporary blip in network connectivity, while one that is consistently too long introduces inefficiencies into the end-to-end process. We should categorize our wait logic using shorter, aggressive timeouts for expected UI transitions and slightly longer intervals for processes known to involve complex database queries or external API calls. Furthermore, if a wait stage fails to satisfy its conditions within the allotted time, it should not blindly proceed. Instead, we must route the execution path to alternative logic, such as an exception handling routine designed to refresh the screen, retry the operation, or log a descriptive error regarding the interface state. This approach ensures that our automation is not just fast, but fundamentally robust against the reality of enterprise software environments. Best practice necessitates that we place a wait stage immediately following any action that induces an application state change. By consistently anchoring our navigation in these synchronization checkpoints, we eliminate the need for guessing the timing of an application response. It is also beneficial to stack conditions logically, ensuring the most critical interface elements are given priority in the evaluation order defined within the stage. When we treat the user interface as a living, dynamic environment rather than a static map, we move away from brittle code and towards sustainable enterprise-grade robotics. As we continue to refine these interactions, remember that the goal is to make the robot appear to move with the same fluid awareness as a human user. This depth of synchronization is exactly what distinguishes a professional developer from a casual observer, ensuring our automations remain stable through updates and environmental shifts. See you in the next lecture. Welcome back to our journey through the Blue Prism Object Studio. In this lesson, we will focus on the fundamental mechanics of interacting with external applications using the read, write, and navigate stages. The interaction layer of any Blue Prism business object relies on three primary stages that translate your logic into tangible system actions. When we talk about the write stage, we are referring to the mechanism for passing input values into the UI elements we have previously defined in Application Modeler. You must configure these stages by selecting the correct element from the Explorer tree and choosing the appropriate action, such as global send keys or simple text entry. It is a common mistake to overlook the necessity of clearing existing data before writing, so always consider utilizing the clear action where the target interface supports it. When dealing with checkboxes or drop-down lists, the write stage acts as the bridge between your data items and the application state. By specifying the index or the specific value, You ensure that the application reflects the desired configuration, provided the element was spied with sufficient precision. Always keep in mind that the right action triggers standard application events, meaning the target application must be in a state ready to accept input, such as having focus or being unlocked. The read stage is effectively the eyes of your automation, allowing you to extract information from the UI that will subsequently influence your process logic. This process involves selecting a target element and choosing an attribute or property, such as text, check status, or visibility, and mapping that result directly into a Blue Prism data item. If you're working with grid components, the read stage provides specialized functionality to pull entire table outputs into collections, which is essential for data-driven processes. You should treat the data retrieved in a read stage as inherently untrusted, meaning you must validate the output format before passing it into subsequent calculations or decision stages. Extracting attributes like the background color or specific HTML tags can also be a powerful way to infer the internal state of a web-based application when standard properties are unavailable. Maintaining clean data flow requires you to be disciplined about the types, as a mismatch between the retrieved data and your variable container will often result in a runtime exception during the execution phase. Efficient automation often hinges on reading only exactly what is required rather than dumping entire object models into memory, which helps keep your runtime footprint lean. While read and write stages manage data, the navigate stage is responsible for the behavioral flow of the application during an automation routine. This stage is remarkably versatile. It handles everything from basic mouse events like clicks and double clicks to complex interactions such as window management and keystroke sequences. When you need to simulate a user pressing a button, the navigate stage allows you to configure a global mouse click, which effectively interacts with the application regardless of its current window focus. You can also utilize this stage to control the application frame itself through commands to maximize, minimize, or close windows, which is crucial for resetting an environment after a failed process run. For keyboard-heavy interfaces, the navigate stage enables you to send specific key combinations that standard text input cannot replicate, such as function keys or modifier keys like Control or Shift. I encourage you to think of the navigate stage as the command center for your object's behavior, orchestrating the transition between the various states the UI might inhabit. By strictly isolating these behavioral interactions within the navigate stage, you ensure that your business objects remain modular and easier to debug when the underlying third-party application inevitably changes its structure. See you in the next lecture. Welcome back. In this lesson, we will examine region mode and the broader challenges associated with surface automation in Blue Prism. Surface automation is undeniably a last resort technique, yet it is essential when you encounter applications that lack accessible object models. When Blue Prism cannot hook into the internal structure of an application, such as a legacy Citrix environment or a mainframe terminal emulator, we must treat the screen as a canvas of pixels rather than a collection of interactive elements. Region mode allows us to map specific coordinates on the screen and define them as functional entities. We begin by defining the top-level application boundary, which serves as the container for our elements. Once this is established, we create localized regions within the application modeler by manually selecting areas of interest on the target interface. This process is inherently brittle, as it relies on the expectation that the application will always appear in the exact same location and orientation, making the stability of the host environment a primary concern. Configuration of these regions revolves around image matching and tolerance settings, which dictate how sensitive the bot is to visual changes. We must define the match index and tolerance levels carefully to ensure that minor background variations or slight shifts in rendering do not cause a failure in the automation. Because we are no longer interacting with underlying code, the bot must interpret the visual output. This is where optical character recognition engines become invaluable. By pointing an OCR-enabled read stage at a specific region, we attempt to translate visual pixel patterns into actionable string data. You will find that the effectiveness of this approach varies significantly depending on font clarity, background contrast, and the specific search algorithm employed by the engine. It is not a precise science, and a significant portion of your development time will be spent tweaking these settings to achieve a reliable success rate. When we interact with these regions, we are effectively sending global events, such as mouse clicks at specific coordinate offsets or keystrokes sent to the active window. Since the object model is invisible to us, the navigate stage must be configured to click at specific X and Y coordinates relative to the region anchor. This introduces the problem of screen resolution and scaling constraints, which can silently break your automation if the runtime resource runs at a different DPI than your development machine. I strongly suggest that you implement design workarounds to mitigate these risks, such as forcing application windows to specific sizes and positions using a base navigation action before starting any interaction. Consistent window placement is just as important as the logic within your object, as it serves as the foundation for the coordinate-based clicks that surface automation relies upon. Weight conditions in a surface automation context require a fundamentally different strategy than what you might be used to with standard Windows or web controls. Instead of waiting for an element to exist in the tree, we must rely on image-based weight conditions, checking for the appearance of specific visual confirmation clues. This might be the appearance of a loading spinner, a specific color appearing in a region, or the presence of text extracted via OCR that signifies the completion of a process. This creates a more fragile interface environment where delays and network latency can cause significant frustration. Developers must build in sufficient buffer times and robust retry loops to handle instances where the image match fails due to a momentary flicker or rendering lag. By keeping your regions as small as possible and centering your logic around visual anchors rather than static coordinates, you can build a more resilient foundation for these non-standard integrations. See you in the next lecture. Welcome back. In this chapter, we will explore the techniques required to design modular, maintainable, and readable flowchart logic within Blue Prism. Building software is rarely about writing a single, long sequence of instructions, and the same principle applies to Blue Prism development. When we model business processes, the tendency is often to dump all logic onto the main page, resulting in a monolithic flowchart that becomes difficult to debug and even harder to read. To avoid this, we must embrace the concept of decomposition, where complex workflows are broken down into smaller, focused subpages. Think of a subpage as a function or a method in traditional programming. It should have a single responsibility. By modularizing our logic, we not only improve the clarity of the process, but also create reusable components that can be invoked from different parts of the automation. Maintaining a clean visual layout is just as important as the logic itself, as it directly impacts our ability to troubleshoot issues effectively when the process is running in a production environment. When we design these subpages, we have to pay careful attention to their interface, specifically inputs and outputs. Blue Prism manages this through page-level scope and explicit argument passing, which ensures that data flows predictably from the main page into a subpage and back again. When you define an input, you are establishing a contract. The subpage promises that as long as it receives the required data, it will perform its specific task. Similarly, output parameters act as the return values, allowing the subpage to communicate the result of its operations back to the caller. We must treat these arguments with care, avoiding global data items whenever possible, as excessive reliance on global scope leads to tight coupling and unpredictable side effects. By keeping the interface clean and clearly defined, we ensure that subpages remain black boxes that can be tested in isolation, which is a hallmark of robust architectural design. The visual representation of our flowchart is effectively the documentation for our automation, so we should treat a cluttered diagram as a technical debt. We generally aim for a consistent flow, typically moving from top to bottom or left to right, which helps the eye follow the logic without unnecessary cognitive load. One common pitfall is the indiscriminate crossing of link lines, which confuses anyone trying to trace the path of execution during a review. By utilizing subpages, we naturally reduce the density of our links, as the complexity is hidden within the pages themselves rather than being displayed on a single, messy canvas. If you find yourself constantly dragging stages to create space for new logic, it is usually a sign that the current page is doing too much and should be split into smaller, more manageable units. Always strive for a layout that is logically grouped, where linked stages represent a coherent business transaction rather than arbitrary steps. Finally, we must consider the security and efficiency of argument passage within our architecture. Every time we pass a large collection or a sensitive piece of data between pages, we should keep in mind that the process is moving these values across the internal process boundary. Secure coding practices dictate that we minimize the exposure of sensitive data items and avoid unnecessary copying of complex objects if a simpler reference will suffice. By adopting a top-down design strategy where the main page serves as a high-level orchestration layer, we keep the implementation details tucked away where they cannot be accidentally altered by unrelated parts of the process. This disciplined approach to structuring complex flows allows us to build solutions that remain stable even when business requirements evolve over time. Our goal is to create a process that reads like a story, where the sequence of pages clearly communicates the underlying business rules to anyone reviewing the code. I look forward to discussing the specifics of calculations in our upcoming session. Welcome back. In this lecture, we will explore the mechanics of the calculation stage and the nuances of building robust expressions within Blue Prism. The calculation stage serves as the primary engine for data manipulation within your process flow, allowing you to transform raw inputs into meaningful business outcomes. When you drag a calculation stage onto the canvas, you are not merely assigning a value, you are defining a formal contract for how data evolves as it passes through your process. I often prefer to treat these expressions as small pieces of logical code that demand clarity, as a poorly constructed formula acts as a ticking time bomb in production. At its core, the expression editor provides access to a comprehensive library of functions ranging from text manipulation and numeric arithmetic to complex date-time operations. Understanding how to leverage these built-in utilities is essential, but equally important is knowing the limitations of the environment in which these expressions execute. By mastering this stage, you move beyond simple variable assignment into the realm of designing self-documenting data transformations that are easier to debug when things inevitably go wrong. When dealing with data, explicit type conversion is a discipline that separates the amateur from the professional developer. While Blue Prism often attempts to implicitly coerce types, relying on this behavior is a gamble that frequently yields unexpected runtime exceptions. I recommend using the built-in conversion functions whenever there is ambiguity, ensuring that your strings and numeric values are treated exactly as the subsequent stages expect. This practice is particularly vital when integrating with external systems that lack the robust type-checking features found inside a development environment. Furthermore, addressing null or undefined values is a non-negotiable requirement for resilient automation. A null value passed into a mathematical expression will almost certainly halt your process, so always validate inputs using the isNull function before attempting to perform any operations. The architecture of your expression itself warrants careful consideration regarding both readability and long-term maintenance. When faced with complex logic, developers often fall into the trap of creating one massive, nested expression that becomes impossible to decipher during an incident review. Instead, favor breaking nested functions into discrete steps or cascading calculation stages, which allows you to inspect intermediate values during testing. If you must use complex formulas, treat them like code and provide context. Although the expression editor itself is limited, you can often document the intent of the logic within the description fields attached to the stage. This defensive approach to design pays dividends when you need to hand over the repository to other colleagues or when you return to the code months later to implement requested changes. Performance is another dimension that is frequently overlooked until it becomes a bottleneck in large-scale deployments. While individual expressions are typically processed in milliseconds, performing thousands of transformations within a loop can accumulate significant latency if those expressions are unnecessarily convoluted. Optimize your approach by keeping calculations simple and minimizing excessive type conversions inside high-frequency loops. If you find your expressions are becoming the focal point of performance issues, consider whether the data could be prepared or cleaned before entering the main loop of the process. Always test your logic with edge cases, such as extreme numeric values or empty strings, to ensure that the environment handles these scenarios gracefully without requiring manual intervention from a human operator. Maintaining a clean and predictable data state is the cornerstone of a stable robotic process architecture. When you configure a calculation stage, you are expressing a logical intent that must hold true across a variety of runtime environments. By focusing on explicit conversions, robust null handling, In a modular approach to complex logic, you insulate your process from the subtle variations in external data quality. Remember that the goal is not merely to get the expression to compile, but to ensure that it functions reliably as part of an integrated, scalable system. Treat every calculation as a unit of business logic that contributes to the overall stability of your implementation. See you in the next lecture. Welcome back. Today, we are going to dive deep into the mechanics of data management within Blue Prism and how variable visibility defines the structure of your automation. In Blue Prism, data items serve as the fundamental building blocks for state management, acting as containers that hold information during the execution of a process or a business object. Each data item must be assigned a specific data type, which acts as a contract between the data and the stages that interact with it. We have a rich set of types at our disposal, ranging from simple primitives like text, numbers, and flags, to more specialized types like dates, times, and structured binary data. When you configure a data item, you are essentially defining the expected schema of that variable, which allows the runtime engine to perform essential type checking before operations occur. This type safety is not merely a feature, but a safeguard that ensures your calculations and data manipulations remain predictable. For instance, attempting to perform arithmetic on a text-formatted number will result in a runtime exception, highlighting why choosing the correct data type. By being explicit with our types, we reduce the surface area for logic errors and create a self-documenting implementation where the intent of the data is clear to anyone inspecting the process diagram. The concept of scope is perhaps the most significant architectural constraint you will encounter when managing data items in Process Studio. When you place a data item on a specific page, its visibility is inherently limited to that page, which we refer to as local scope. This design choice follows the principle of encapsulation, ensuring that the internal calculations or temporary state of one page do not leak into another, thus preventing side effects. However, there are scenarios where data must transcend page boundaries, requiring the use of global scope or parameters. By configuring a data item to be exposed, you transform it into a parameter that can be passed between parent and child pages, effectively creating an interface for your logic. This is essential for modularizing your process, as it allows you to pass inputs into subpages and receive outputs back, rather than relying on global variables that are visible everywhere. While the temptation to make everything global might be strong for beginners, maintaining the smallest possible scope is a hallmark of defensive programming that prevents naming collisions and makes debugging significantly easier. Initialization and default values represent a common trap for developers who overlook how the life cycle of a process affects state. A data item will initialize with its default value whenever the process or page scope is entered, which is an important detail when looping or re-entering pages. If you intend for a counter or a flag to persist throughout the entire execution, you must ensure it is defined at the main page level or managed via a persistent persistence layer like a work queue. Tracking the value of a variable throughout the process lifecycle requires disciplined naming conventions to avoid collisions, especially in complex processes with dozens of pages. I recommend adopting a prefixing strategy for your data items to distinguish between configuration parameters, temporary working variables, and business data. When dealing with sensitive information, such as credentials or private customer data, you should utilize the password data type, which masks the value in the user interface and protects it from being logged in clear text. This practice is not just a security requirement, but a responsible approach to handling operational data in a production environment. Managing dependencies and exposure parameters requires a thoughtful approach to design, particularly when you are building reusable components. When you mark a data item as a parameter, you essentially define an entry point for your subprocess, allowing the caller to inject values at runtime. This capability is what enables the high degree of flexibility expected in modern RPA solutions, as it allows you to decouple the data from the workflow logic itself. You should aim to design your subpages in a way that minimizes their reliance on the global state, preferring instead to take required information as arguments. This shift towards parameterization facilitates testing, as each page becomes a functional unit that can be verified in isolation with defined inputs and outputs. When configuring these parameters, always define the direction as either input, output, or both. which further documents the interface and prevents accidental mutation of data that should remain read-only. By adhering to these naming and scoping conventions, you build processes that are not only robust but also maintainable by your peers. As you continue your journey, keep focusing on how these data items interact with the broader flow of your automation. See you in the next lecture. Welcome back to our journey through Blue Prism development. In this session, we will deep dive into advanced collection manipulation and the efficient use of loop stages. Collections represent the primary mechanism in Blue Prism for handling multi-row, multi-column data structures, acting essentially as an in-process table. When we define a collection, we are establishing a schema that dictates the data types and column names available for our logic. You can populate these via utility actions, such as converting a CSV file into a collection, or by capturing outputs directly from other stages like database reads or application modeler actions. Because collections reside in memory, they are highly performant for intermediate data processing, but they require discipline in how they are initialized and cleared. Always define your schemas explicitly, rather than relying on inferred types, if you want to ensure your process remains resilient against upstream data changes. The heart of our data processing logic almost always involves the loop stage, which iterates through every record currently held within a target collection. When you configure a loop, you define the collection that serves as the iterator, and Blue Prism automatically tracks the current index for you. To access the values within the current row, you utilize dot notation, which follows the pattern of collection name. Field name. This simple syntax provides a direct window into the data properties, allowing you to pass values from the collection into downstream calculation or write stages. If you find yourself performing complex logic inside a loop, keep in mind that the current row remains fixed until the loop exits or iterates to the next record. Nesting loops is a common scenario when you need to perform relational operations, such as comparing a master collection against a transactional one. While Blue Prism handles nested loops effectively, you must remain conscious of the exponential growth in execution cycles as the nested depth increases. Ensure that inner loops process the smallest possible sets of data relative to the outer loop to keep your execution speed within acceptable business parameters. If you need to transform or augment data, you can append rows dynamically using the collection modification utility. But be wary of doing this while the loop is still iterating over the same collection. Appending to a collection while iterating through it can lead to unexpected infinite loops or corrupted state, so it is safer to write results to a secondary temporary collection before merging them. Filtering records is another operation frequently required to narrow down a dataset before you begin intensive processing. Rather than manually looping and checking conditions to build a new set of data, you should look toward utility actions that can perform in-memory filtering. By keeping your collections clean of unnecessary records as early as possible, you significantly reduce the memory footprint and the number of cycles your robot spins in idle iteration. Always verify the status of your collection memory by using the clear action at the appropriate cycle points, such as before starting a new batch process. Unmanaged memory growth in long-running processes is a frequent source of performance degradation, even within otherwise well-structured automations. Optimizing your looping logic is the difference between a process that completes in minutes and one that hangs indefinitely. Think of your data flow as a pipeline, where each iteration is a discrete unit of work that should be treated as atomic as possible. Avoid heavy operations like constant environment reads or deep application modeler queries inside the loop body, as these will multiply the latency by the number of rows in your collection. Instead, try to cache required configuration values into a local data item before the loop execution begins. This simple architectural shift ensures that your loop maintains a high throughput by focusing exclusively on data translation and business logic rather than auxiliary lookups. See you in the next lecture. Welcome back. In this lesson, we will focus on the fundamental mechanisms for controlling process flow via decision and choice stages, which are essential for creating intelligent automation logic. The decision stage represents the simplest form of conditional routing in Blue Prism, functioning as a binary gatekeeper for your process flow. When you configure this stage, You provide a single logical expression that the Blue Prism runtime evaluates at execution time. This expression must resolve to a Boolean value, meaning either true or false, which then dictates which branch the object or process follows. Because this is a binary operation, it is most effective for simple checks, such as verifying if a data item is empty, comparing two strings, or checking if a specific numeric threshold has been met. From a maintainability perspective, it is critical to keep the expressions inside these stages as readable as possible to ensure that any developer reviewing your code can quickly grasp the business rule being enforced. If you find yourself constructing overly complex logical chains within a single decision stage, it is often a sign that you should rethink your design and potentially break the logic into smaller, more granular checks. Remember that every time a process flows through a decision stage, the outcome is recorded, making these stages vital checkpoints for both auditability and debugging during complex process execution. When a scenario requires evaluating more than just a binary condition, the choice stage serves as a much cleaner and more readable alternative to nested decision stages. Think of the choice stage as a multi-way switchboard that evaluates a series of conditions sequentially until it encounters the first one that evaluates to true. You define one or more conditions, each associated with a specific exit point from the stage, allowing the workflow to transition directly into the appropriate logic path. A key requirement when using the choice stage is the mandatory implementation of an otherwise path, which acts as a catch-all mechanism if none of the explicit conditions are met by the runtime environment. This structure is superior to daisy-chaining multiple decision stages because it significantly improves the visual layout of your process diagram and prevents the spaghetti code effect that occurs when logic is nested too deeply. By using choice stages for mutually exclusive conditions, you effectively document the business requirements directly within the flow, making the configuration self-explanatory for anyone auditing the process later on. Always ensure that your conditions are ordered logically, perhaps by the frequency of occurrence or the priority of the business outcome, to optimize the performance of the evaluation loop. Structuring your rule evaluations effectively is less about the tool itself and more about how you represent the business requirements in code. When you are designing your process flows, aim for a clear, linear progression that minimizes back and forth movement across the page workspace. If you discover that your logic requires checking the same data multiple times across different branches, consider calculating the state of that data once and storing it in a variable before reaching the branching logic. This approach reduces redundant calculation processing and presents a cleaner, more robust architecture that is easier to unit test and maintain over the lifespan of the automation project. Furthermore, strive for comprehensive coverage where every possible business state is accounted for, either through explicit logic paths or clearly defined otherwise paths that initiate error handling or logging. By treating conditional routing as a tool for creating deterministic outcomes rather than just a way to shape a flowchart, you elevate the quality of your Blue Prism solutions. The goal is to reach a point where the logic flows as predictably and as clearly as a well-written series of if-else statements in a standard programming language. See you in the next lecture. Welcome back. Let us explore the core principles of optimizing process performance and resource utilization within the Blue Prism ecosystem. When we approach the optimization of a Blue Prism process, we must first shift our perspective from merely functional code to performance engineering. Many developers view automation as a sequence of stages that simply need to return a correct result, but true mastery involves understanding the hidden costs of every interaction. A sequence of read stages might look elegant in Process Studio, yet each one represents a network round trip that consumes precious milliseconds. When you scale this across hundreds of records, these silent accumulations become significant bottlenecks that impact the total cycle time. You should always aim to minimize these interactions by evaluating the necessity of each stage. If you can perform a calculation or a transformation in memory within a single action, avoid reaching out to the target application multiple times. Redundant calculation stages are a common source of technical debt that silently degrades system performance over time. We often see patterns where developers evaluate the same expression across multiple subpages or within tight loops, unnecessarily consuming CPU cycles. Instead of recalculating a value, store the result in a well-scoped data item and propagate that state through your process flow. Similarly, examine your subpage nesting depth, as excessive recursion or deep call stacks can increase the complexity of your execution path and make debugging logs harder to parse. A shallow, linear call structure is almost always easier to maintain and faster for the runtime resource to interpret during execution. Think of every subpage call as a slight tax on your orchestration engine that should only be paid when absolutely necessary. Collection loops are the engine room of high-volume processing, yet they are frequently configured in ways that introduce systemic lag. When iterating through a collection, ensure that you are only performing essential operations within the loop body. If you need to filter or sort data, try to perform those operations using a custom code stage or a robust expression before entering the loop itself. Also, be mindful of the memory footprint of your collections, as failing to clear or reset collections can lead to gradual memory leaks during long-running sessions. By keeping your data structures lean and recycling their memory appropriately, you prevent the runtime resource from experiencing garbage collection spikes. Efficiency is found in the discipline of managing state throughout the entire lifecycle of the process. Application synchronization is perhaps the most delicate aspect of performance tuning, where the desire for speed must be balanced with the requirement for stability. We often rely on wait stages, but overuse of these stages or improper configuration can lead to bloated execution times. Be precise in identifying the state change you are monitoring, and avoid blanket timeouts that keep the robot idle longer than necessary. You should also audit your use of stage delays, as these artificial pauses are often symptomatic of a design flaw rather than a legitimate architectural requirement. If you find yourself adding wait times to fix a synchronization issue, you are likely masking an unreliable interaction that should be addressed at the application modeler level. Aim for event-driven synchronization whenever the target application supports it, rather than relying on time-based approaches. Finally, we must consider the broader architectural impact of data caching and cross-network communication. Every time a robot queries a remote server or a database, it is susceptible to network latency and server-side throttles. Implementing a centralized data cache for frequently used static information can drastically reduce the number of redundant calls and shave significant time off your process execution. When dealing with enterprise environments, adhere to high-performance design patterns that emphasize asynchronous processing and parallel workflows where possible. By being intentional about when you read, write, and wait, you transform your automations from simple scripts into enterprise-grade assets capable of sustained, high-speed performance. Always profile your process with a focus on where the physical interaction meets the logical flow. See you in the next lecture. Welcome to this section on advanced exception handling, where we will focus on building robust automation through the strategic use of recover and resume stages. In the world of software development, we often strive for the happy path, where every step executes according to our initial assumptions. However, enterprise environments are inherently unpredictable, and external applications will inevitably throw errors, lose connectivity, or return data in unexpected formats. When this happens, we must avoid the temptation to let the process simply fail and terminate, as this leaves the system in a dangling, inconsistent state. Instead, we architect our Blue Prism processes to act as if they are aware of their surroundings, identifying failures the moment they occur and gracefully managing the transition between a broken state and a functional one. This is exactly why the recover and resume combination is the bedrock of professional-grade robotic process automation. If you think of a process studio flow as a continuous line of logic, an exception acts as a sudden severance of that line, effectively stopping the flow dead in its tracks. A recover stage functions as a specialized control structure that intercepts this interruption, preventing the error from bubbling up further than you desire. By placing a recover stage strategically, you create a dedicated trap that catches the exception, holding it in a suspended state that allows you to decide how to proceed. Once the execution enters this recovery branch, the standard sequence of your main logic is effectively paused, giving you the necessary control to perform cleanup operations. I often liken this to a try-catch block in C#, where the intent is not to ignore a problem, but to acknowledge it, log the necessary information, and orchestrate a safe transition back to a stable posture. Once the exception is caught, You enter a phase of damage control where you must decide exactly how to resolve the underlying issue. During this time, the process is still technically in an exception state, meaning that Blue Prism will block any attempt to continue along the main flow until that state has been explicitly cleared. This is the precise moment when the resume stage comes into play as a vital mechanism. You must use the resume stage only after you have performed your cleanup, such as closing a faulty application dialog, clearing insecure data from temporary memory, or resetting a specific system flag to a known starting value. Only then does the resume stage clear the exception from the internal runtime context, effectively telling the environment that the error is handled and it is now safe to resume normal operation. The architecture of your recovery logic should always prioritize the resynchronization of the target application with the current process state. A common pitfall for developers is to trigger a resume stage too early, before the application has actually recovered its responsiveness or before the intended screen has been rendered. If your automation attempts to interact with an application that is still struggling to handle the previous error, you will simply trigger a secondary exception, creating a cascade that makes debugging exponentially more difficult. You should verify the application's state after an error by using mandatory wait stages or by querying the object surface for confirmation. By ensuring that the application environment is perfectly aligned with where you plan to resume the flow, you minimize the risk of intermittent failures during retry attempts or error handling routines. When implementing these stages, remember that once you encounter an exception, the scope of your current logic is essentially tainted. Any attempt to proceed without properly clearing the exception state will only cause the process to continue throwing errors, which is colloquially referred to as an exception loop. Your goal when designing these flows is to provide a clean exit point from the error handler that feeds back into a stable restart condition. This might involve navigating the user interface back to a home screen, clearing local data items that may have been partially populated, or perhaps notifying a human operator that intervention is required. Treat the recovery and resume sequence as a necessary overhead that creates a resilient, industrial-strength automation that can survive the unpredictable nature of real-world enterprise infrastructure. See you in the next lecture. Welcome to this exploration of localized recovery within Blue Prism. In this chapter, we will discuss how to isolate processing vulnerabilities using exception blocks to contain runtime faults without crashing your entire process. When we discuss exception handling, there is often a temptation to rely on a single, global recovery mechanism located at the entry point of a process. While this provides a safety net, it lacks the precision required for robust, enterprise-grade automation. Instead, we use blocks to create specific, surgical zones of control around risky operations. Imagine you are interacting with a volatile web service or performing a complex database write that is likely to fail under load. By placing these specific actions within an exception block, you effectively shrink the scope of potential failure. If an exception occurs within that bounded region, the process does not have to backtrack to the top level of the flow. You can handle the disruption immediately at the site of the fault, perform exactly the cleanup required for that specific step, and continue execution as if nothing happened. This architectural choice significantly reduces the maintenance burden because your error handling logic stays close to the code that generates the potential runtime fault. Drawing boundaries around high-risk stages requires a disciplined approach to how you structure your flowcharts. A block is essentially a visual container that wraps a sequence of stages, and it is governed by a recover stage. When you target specific application interactions or web requests, you create a dedicated pathway for failures related to those specific tasks. The principle here is isolation through scope. If you bundle too many disparate operations into a single broad block, you lose the ability to distinguish between different types of failure. For example, a network timeout during a database query should be treated differently than a validation error in a user interface. By keeping blocks small and focused, you ensure that the recovery logic is specific to the intent of the operations contained within that boundary. This makes your logic clearer to read and much easier to debug when something eventually does go wrong during a production run. Strategic nesting of blocks allows for hierarchical error management where local recovery takes precedence over global handlers. In Blue Prism, an exception will always look for the nearest enclosing block that contains a recover stage. This is a powerful feature because it allows you to handle transient issues locally, perhaps by retrying a connection, before bubbling the error up to a page level or process level handler if the local recovery fails. When designing these structures, you must be careful to avoid overlapping boundaries, as an unclearly defined scope leads to unpredictable behavior during the propagation of an exception. Each block should have a singular, well-defined purpose. If you find yourself needing to catch errors at multiple levels, ensure that the inner blocks perform the specific, fine-grained remediation while leaving the outer, larger blocks to manage broader systemic issues. This creates a layered defense strategy that is much more resilient to the unexpected dynamics of target applications. Maintaining tight control over error propagation across process subpages is a critical skill for any serious developer. When an exception is caught in a local block and subsequently resumed, the process state is effectively cleaned, allowing it to move forward cleanly and predictably. However, if a local exception cannot be resolved, you must decide whether to consume the error or allow it to bubble up to the parent page. You should always aim to minimize the distance an exception travels before it is resolved or rethrown as a meaningful business exception. By implementing precise block-level remediation, you retain the full context of the failure, which is invaluable when monitoring logs later. A well-designed process uses blocks as containers for atomicity. They ensure that even when an operation fails, the state of your application and your data remains consistent and ready for the next iteration. Keep your blocks clean, avoid unnecessary nesting, and always verify that your resume points lead to a stable state. See you in the next lecture. Welcome back. Let's explore the critical taxonomy of errors in Blue Prism. In this lesson, we will establish clear standards for differentiating between system and business exceptions to ensure our automations remain robust and maintainable. When we build enterprise-grade automation, exception handling is not merely a defensive mechanism, but a fundamental architectural requirement. Understanding the distinction between a system exception and a business exception is the primary difference between a fragile process and a production-hardened solution. A system exception occurs when the environment or the application itself behaves in a way that prevents the bot from proceeding regardless of the input data. Think of these as infrastructure-level failures. For instance, a server becomes unreachable, a network timeout occurs during a credential handshake, or the target user interface crashes before a requested element can be identified. These events are outside the scope of the process logic because the bot literally cannot perform its duty due to external technical constraints. In such scenarios, your strategy should focus on recovery, retries, and eventual alerting to IT support teams because the underlying environment is compromised. In stark contrast, business exceptions are triggered when the process logic encounters a scenario that is valid in the technical sense, but invalid according to your specific business rules. If you are processing a mortgage application and a user submits an age that is less than 18, the application form is perfectly functional and the network is responding correctly, but the transaction fails to meet the defined procedural criteria. These exceptions represent the expected variability of real-world data and do not imply that your infrastructure has failed. Business exceptions often involve missing documentation, out-of-bounds inputs, or internal policy conflicts that make the current transaction unprocessable by the bot. Unlike system issues, there is no technical retry that will magically correct a missing document or an invalid policy flag. So the correct path is often to mark the item as an exception and move to the next valid record in the work queue. Configuring these types correctly requires you to categorize them at the design stage, rather than treating every error as a generic failure. When you throw an exception in Blue Prism, the exception type and the exception message serve as the primary diagnostic signals for the human operators managing the control room. For system exceptions, your label should be precise enough for a technical administrator to pinpoint the origin, such as browser failed to launch, or database timeout on query. For business exceptions, the error messages must provide enough context for the business user to perform manual remediation, such as invalid account number format or expired policy document. By keeping these categories distinct, you allow the control room management to filter sessions and perform targeted analysis instead of burying valuable business intelligence under a mountain of noise from unrelated technical flakiness. The decision-making process for handling these exceptions effectively dictates how you design your retry loops and your logging functions. If you choose to implement a retry mechanism, it should be reserved exclusively for transient system exceptions because network errors and UI delays are often temporary in nature. Retrying a business exception is a waste of computational resources, as the data state that caused the error will remain unchanged upon the next attempt. Instead, design your business exceptions to trigger a notification flow that updates the work queue or alerts a specific department to address the missing information. This logical separation ensures that your developers and business stakeholders can distinguish between issues that require a software patch or a system reboot and those that require a change in data handling or organizational procedure. See you in the next lecture. Welcome to this examination of the hierarchical exception bubble-up mechanism in Blue Prism. We will explore how unhandled exceptions migrate through execution layers and how to manage them effectively. In Blue Prism, an exception does not simply vanish when it occurs within a nested subpage or a business object action. Instead, the runtime engine initiates a bubble-up process, effectively moving the exception context up the call stack until it encounters a recovery block. If you have ever noticed that an error in a low-level object suddenly halts your main process, you have witnessed this behavior firsthand. When an exception is raised, the current page execution terminates immediately. The engine then inspects the caller of that specific page to determine if a recovery stage is present to intercept the fault. This propagation continues until the exception is either caught by an active recovery block or allowed to reach the base level of the process, triggering an unhandled exception state. Understanding the anatomy of this propagation is essential for creating resilient automation. When an exception moves from an object level to a process level, it carries with it the original exception details, which are populated in the exception detail and exception type fields. If you fail to use a recovery block in a child page, the parent page becomes responsible for handling that failure. This creates a design trade-off where you must decide whether to handle errors locally or allow them to ascend to a higher level oversight function. Local recovery is often preferred when an action is expected to fail occasionally and requires a specific remediation step, such as closing a specific dialog box or clicking a refresh button. Allowing an exception to bubble up is more appropriate for catastrophic failures that should stop the entire process flow immediately. To implement this effectively, we must consider the structural context of our processes. Imagine a scenario where a complex process calls a subpage, which in turn calls a business object to interact with an application. If the business object encounters a connectivity issue, it raises a system exception. If no recovery block exists within the business object, the exception moves to the subpage. If the subpage also lacks a recovery block, it moves to the main process page. By placing a recovery block at the process level, you can centralize your error handling logic, ensuring that any failure, regardless of deep positioning, hits a unified termination strategy. This keeps your visual flow clean and avoids the redundancy of having identical exception handling logic scattered across dozens of subpages. When you do choose to catch these bubbles, you must be careful not to discard the information contained in the exception. Using the exception detail function within a recovery block allows you to capture the specific source of the failure. Without proper handling, you might catch the exception, but lose the trail of which specific subpage or object actually failed to perform its task. By utilizing the resume stage correctly, you can acknowledge the caught exception, log the necessary diagnostic data, and then gracefully decide whether to retry the action or perform an orderly shutdown of the process. This disciplined approach ensures that your logs remain descriptive and your runtime errors do not leave the system in an ambiguous or half-finished state. Finally, consider the concept of rethrowing exceptions after performing a necessary cleanup. Sometimes you want to catch an exception at a subpage level to save a log or close an application instance, but you still want the parent process to treat the operation as failed. In these instances, you can trigger a new exception in your handler, which effectively replaces or re-emits the failure up the stack. This pattern provides a powerful way to wrap specific low-level errors into more meaningful high-level business reports. Strategic use of the hierarchy is what separates a brittle project that requires constant supervision from one that identifies its own limitations and reports them through the standard operational dashboard. I will see you in the next lecture. Hello, and welcome back. In this session, we investigate how to extract granular diagnostic information from exceptions to maintain system observability and simplify complex debugging workflows. When a process encounters a disruption, simply knowing that a failure occurred is rarely sufficient for a robust production environment. Blue Prism provides a set of built-in functions specifically designed to pull forensic data out of an exception object while the process is in a recovered state. These functions, exception detail, exception type, and exception stage, act as critical diagnostic levers, allowing you to intercept the context of a failure at the exact moment it occurs. Rather than letting an exception vanish into a generic error log, you should programmatically capture these values and funnel them into your logging architecture. This practice transforms opaque failures into actionable intelligence, significantly reducing the mean time to repair for any automated solution you build. The exception detail function returns the specific message associated with the failure, which is especially useful when catching general system exceptions that originate from external application crashes or network timeouts. When used in conjunction with the exception type function, you gain the ability to classify the nature of the issue, distinguishing between transient environmental failures and persistent logic errors. Exception stage allows you to identify the unique ID or the name of the stage where the exception was originally thrown, which is indispensable for tracking the path taken within complex business objects. Think of these functions as a way to read the state of the error before you reach the resume stage, or allow the exception to propagate further. By harvesting this data, you ensure that your audit logs contain meaningful identifiers rather than just vague assertions of process failure. Beyond mere logging, these functions allow you to construct a structured error report that describes the application state precisely at the time of the incident. You can use these values as inputs for administrative notifications, ensuring that support teams receive a contextual summary of the problem instead of a generic system alert. When you capture the call stack or the relevant data item snapshots along with the exception detail information, you are effectively performing self-diagnostics within the runtime environment. This level of detail is a hallmark of professional-grade development, as it moves your error handling from a reactive necessity to a proactive component of your application architecture. Always store these details in a centralized database or an enterprise-grade log aggregator to ensure that you have access to historical data for operational intelligence analysis. The implementation of these functions should always occur within a dedicated recovery block, immediately following the recovery stage but prior to the resumption or rethrowing of the exception. If you wait until after the resume command is executed, the context of the specific exception is lost, and the global exception functions will return empty values. By maintaining a standard pattern for capturing this metadata in every recovery block, you establish a predictable audit trail that remains consistent across all your processes. This consistency makes it significantly easier to create automated reports based on log data, as your error signatures will always adhere to a known, structured format. Focusing on the durability of your error logs is as important as the logic of the automation itself, particularly in large-scale deployments. The goal is to eliminate guesswork by providing developers and maintainers with the same context that the robot possessed at the time of the failure. By standardizing the capture of exception detail, exception type, and exception stage, you are not just handling errors, you are instrumenting your code for long-term sustainability. This approach ensures that your processes are transparent and that any deviation from the expected path is documented in a way that respects the complexity of the enterprise environment. Taking the time to build these diagnostic bridges now will pay dividends when you are tasked with maintaining these processes in production under tight service level agreements. Remember that observability is not an afterthought, but rather a fundamental requirement of any scalable Blue Prism design pattern. I will see you in the next session. Welcome back to our exploration of advanced automation design patterns within Blue Prism. In this session, we investigate the architecture of resilient retry patterns, which are essential for gracefully handling transient faults in connected systems. When an automated process interacts with external applications or web services, intermittent network latency or momentary unavailability of the target interface can produce failures that appear as system errors. If we simply allow an exception to propagate without intervention, the process will fail prematurely, requiring manual handling that defeats the purpose of end-to-end automation. Instead, we must construct a wrapper around the operation that attempts the sub-process multiple times before escalating to a formal exception. This strategy shifts the focus from brittle, single-attempt logic to a stateful approach that respects the volatile nature of managed services. By implementing these patterns, we ensure that our bots remain robust against the minor, short-lived disruptions that characterize modern enterprise environments. To implement this, you must first define a dedicated state container, typically a data item acting as a counter, to track the number of failed attempts within your loop structure. It is vital that this retry count mechanism resides outside the local scope of the primary action block to ensure it persists across multiple loop iterations. You should establish a clear threshold for the maximum number of attempts allowed for a given operation to prevent infinite execution cycles. As your process logic enters the retry cycle, configure an exponential back-off interval, which involves incrementally increasing the wait time between each subsequent attempt. By applying a back-off strategy, you give the target system a period of relative quiet to recover its resources, which is significantly more effective than rapid-fire polling that could potentially trigger rate-limiting policies or further lock out the application. Resilience extends beyond simple timing concerns. It also requires explicit state management when a component fails. If an application session becomes unresponsive or demonstrates erratic behavior following a failed action, it is necessary to perform a clean reset of the environment. This means closing the current instance of the application process and launching a fresh session before the next retry attempt commences. By resetting the target interface to a known baseline configuration, you eliminate the risk of residual object state, such as stale browser cookies or blocked dialogues, interfering with the subsequent attempt. This rigorous approach to cleanup is what separates production-grade automation from simple scripts that only function under ideal theoretical conditions. When you effectively wipe the slate clean between retries, you provide each new attempt with an equal, predictable probability of success. One of the most consequential design choices you will face is distinguishing between transient system errors and permanent business data errors. The retry logic must be strictly constrained to transient issues like network timeouts, temporary API rate limiting, or memory-related interface stalls. You must explicitly catch these system exceptions and trigger the retry flow, while allowing business exceptions, such as invalid input data or missing mandatory fields, to bubble up immediately without attempting a retry. If you apply a retry mechanism to a permanent data error, you create a logically broken loop that wastes compute resources and misleads log analysis by obscuring the true cause of the process failure. Always implement a decision stage immediately after the recovery block to validate the exception type, ensuring that your automated response matches the nature of the underlying problem. See you in the next lecture. Welcome back to our journey through the Blue Prism developer ecosystem, where we now turn our attention to the configuration of work queues within the system manager. In this chapter, we will master the essential settings that allow for robust, scalable transaction processing across your digital workforce. When we approach the System Manager tab to define a work queue, we are essentially building the foundation for how our robots perceive, prioritize, and manage the flow of unit work. The queue name serves as the primary identifier for your business process, so consistency here is not merely a formality, but a necessity for long-term maintainability. When setting up these queues, you will encounter the option to define key fields, which act as a composite index for your transaction items. By designating specific data fields to serve as keys, you allow the control room and other management utilities to uniquely identify transactions without needing to traverse every piece of metadata within the underlying database. This is particularly useful when you need to audit specific transaction strings or query the queue state programmatically during a runtime session. A critical decision point during the creation of a work queue involves the implementation of encryption for data at rest. Within the configuration panel, you are presented with options to specify whether sensitive item data should be encrypted before it is persisted into the database. While this may add a slight overhead to the database write operations, the trade-off is essential for meeting compliance requirements and operational governance policies regarding the handling of sensitive customer information. Once you enable encryption, Blue Prism utilizes the configured runtime encryption keys to obfuscate the data. You must ensure that your environment security baseline aligns with these settings to prevent unauthorized access to the queue data should the database logs or backups be inspected outside of the Blue Prism application layer. Status tracking and retry logic configurations form the backbone of a resilient automation. When you define the maximum number of retry attempts for system exceptions, you are essentially establishing a boundary for how much environmental variance your process can tolerate before it escalates to a human operator. Providing a sensible number here prevents infinite loops in cases of transient connectivity issues, while ensuring that valid issues are logged as deferred or marked with an exception. Beyond retries, you must choose the appropriate distribution model for your work items, specifically whether standard first in first out logic is sufficient or if you require priority-based distribution. Priority-based queues allow you to influence the order in which items are served to robots, which is invaluable when dealing with time-sensitive SLA-driven processes where some transactions carry more weight than others. Designing for multi-robot environments requires a careful alignment between queue configuration and actual process architecture. When multiple runtime resources pull for work from the same queue, the potential for race conditions or resource contention increases if the queue isn't configured for concurrent throughput. You should evaluate the transaction volume and the average execution duration of your processes to determine if a single, larger queue is more appropriate or if a strategy of partitioned queues is required to balance the workload. Proper configuration in the system manager ensures that these runtime resources remain synchronized and that the distribution engine effectively manages the load, adhering to your established infrastructure policies. By mastering these configurations, you move from simply building bots to architecting enterprise-grade solutions that stand up to the rigors of production environments. I will see you in the next lecture. Welcome back. In this lecture, we focus on the transactional mechanics of Blue Prism work queues by mastering the add to queue and get next item actions. When we transition from simple automation to enterprise-grade solutions, the shift often revolves around how we manage data at scale. Blue Prism handles this through work queues, which act as the central nervous system for decoupled transactional processing. To push data into a queue, we rely on the internal work queue business object, specifically the add to queue action. This action takes a collection that you have filtered or prepared in your process and maps it into the queue structure, where Blue Prism automatically generates a unique item ID for every row. This identifier becomes the primary key for tracking the lifecycle of that specific transaction throughout its journey in the environment. By utilizing collections early in your workflow, you ensure that the data is structured correctly before it ever touches the queue, which is a fundamental pattern for keeping your processes robust and audit-ready. Once your queue is populated, the responsibility of the digital worker shifts toward consumption, which we achieve using the getNextItem action. This is not merely a method to pluck the next available record. It is a highly controlled interface that enforces transaction integrity across your entire pool of available resources. When a process calls this action, the Blue Prism runtime engine evaluates the pending items based on their defined priority and their arrival time in the queue. Crucially, the action acts as a lock, marking the specific item ID as exclusively owned by the requesting session. This locking mechanism prevents multiple robots from attempting to process the same transaction simultaneously, thereby ensuring that your workload remains consistent even when you scale to a large farm of runtime resources. A common point of failure for developers new to queue orchestration is the handling of the scenario where no items remain in the queue. In a well-structured production process, your logic should anticipate this state rather than treating it as an unexpected error. When the getNextItem action returns a result indicating that no further pending items exist for the specified queue, your flowchart should naturally guide the process toward a graceful conclusion. This involves a clean shutdown cycle where you perform necessary logging, release any held application handles, and ensure the robot enters an idle state or ends the session according to your resource configuration. By designing this path intelligently, you avoid unnecessary exceptions or orphan sessions that can clog your control room and skew your operational performance reporting. Managing these transitions effectively requires a deep understanding of the scopes and triggers involved in your process model. You should always treat the data object returned by the getNextItem action as the primary container for your current work unit. If you find yourself frequently using global variables to pass data between stages after a queue item has been fetched, it is usually a sign that your architecture needs refactoring. Stick to the item-level data provided by the queue, as this keeps the state confined to the process instance, which is critical for retry logic and general debugging. By focusing on these transactional building blocks, you ensure that your automation can handle thousands of items with the same predictability as when it handles just one. See you in the next lesson. Welcome back, and let us now explore how to implement tagging and deferring items to enhance your work queue management. Effective work queue management is rarely about processing a flat, uniform list of tasks in a blind sequence. In any non-trivial automation scenario, you will encounter situations where transaction items need categorization, special handling, or temporary reprioritization based on the state of the target application. Blue Prism provides the tagging and deferral mechanisms precisely to solve these architectural challenges. Without these tools, a developer is forced to rely on external database lookups or complex brittle logic within the Process Studio flow itself. By embedding this business logic directly into the queue management lifecycle, you gain the ability to create dynamic, self-routing workflows that react intelligently to the data they hold. This approach not only improves the robustness of your automation, but also significantly simplifies the governance and auditability of your transactional processing paths. Tagging acts as a metadata layer attached to individual work items, allowing you to slice and dice your queue at runtime. When you use the tag item action, you are effectively applying a label to a record that persists for the lifetime of that item. These tags are not just static markers. They serve as powerful filters within your getNextItem stage. By specifying a filter expression in the action parameters, you can selectively pull items with specific tags, which immediately enables a pattern where one single queue can be serviced by multiple specialized worker processes. Imagine a scenario where a process must handle both urgent customer requests and standard operational tasks. Instead of creating two separate queues, you tag the urgent items, allowing your primary bot to prioritize those specific tasks while secondary processes handle the backlog. This dynamic routing reduces the surface area of your queue configuration and keeps your architecture clean and maintainable. In addition to categorization, the defer item action provides a mechanism to synchronize your automation with the inherent latency of external systems. Frequently, a bot will process a transaction only to realize that the downstream application or a human colleague needs a specific amount of time to complete their part of the workflow. Instead of throwing a business exception or consuming system memory by looping and waiting, you can simply defer the item until a future timestamp. When you call the defer item action, the queue item is moved to a deferred state where it is invisible to any getNextItem requests until the specified time elapses. This is a design pattern that respects the state transitions of the external environment rather than fighting against them. It prevents the infinite loop of retry scenarios and ensures that your robots remain efficient by only picking up items that are truly ready for action. Integrating these features requires a clear understanding of how these flags influence the overall state machine of the queue. If you apply a tag, you are modifying the metadata, but you are not changing the fundamental status of the item. Conversely, deferring an item locks it from the queue's perspective until the runtime clock surpasses your set threshold. You must be careful to handle any potential collisions between tags and deferral intervals, as complex filtering logic can sometimes inadvertently exclude items that you intended to process. Always design your tag strategy to be idempotent and descriptive, avoiding nebulous labels that might confuse other developers who maintain the system after you. By mastering these two primitives, you move beyond simple, linear task processing and into the realm of designing intelligent, responsive middleware that manages business transactions with precision and intent. See you in the next lecture. Welcome back to our exploration of Blue Prism Work Queue Management. In this lesson, we will focus on the tactical orchestration of item priorities and the granular tracking of transaction states within the control room. When we design automated workflows, we often treat queue items as a first-in, first-out sequence, but real-world business requirements rarely align perfectly with that baseline assumption. Service-level agreements often mandate that specific transactions, perhaps those involving high-value accounts or urgent compliance deadlines, must be processed ahead of routine tasks. Blue Prism handles this by allowing developers to assign a numerical priority to work queue items during the initial ingestion phase. When a process calls the Get Next item action, the underlying infrastructure automatically selects the work item with the highest priority value, provided that the item's status is pending and it has not been deferred. This numerical sorting means that a priority value of 1 will be addressed before a value of 100, effectively allowing you to inject urgency into your batch processing without rewriting your entire logic flow. Beyond simple ordering, we must maintain visibility into the life cycle of each transaction through status tracking. The update status action is not merely a logging convenience, it is a critical instrument for providing business stakeholders with a transparent view of the work being performed. By updating the item status string at distinct milestones throughout your subpages, you transition from opaque in progress states to descriptive stages like validation completed or pending external appraisal. This approach transforms your control room from a simple monitoring console into a real-time dashboard that reflects the actual business state of the workload. When an operator views a queue, they should intuitively understand exactly where a bottleneck exists simply by observing the distribution of items across these specific statuses. Monitoring the health of your queue involves more than just watching items move from pending to completed, as you must also interpret the metrics provided by the control room views. By focusing on queue depth, you identify spikes in volume that may require additional runtime resources to prevent a violation of your SLA commitments. Processing velocity, calculated by the rate at which items are reconciled against your total current volume, serves as a leading indicator of whether your current scheduling strategy is sufficient. If you observe that the average handle time for specific item types is increasing while the queue depth grows, you are likely facing a resource contention issue or a degradation in the latency of an external application. These indicators are the primary signals that trigger an operational shift, such as scaling your resource pool or reprioritizing the existing backlog to favor high-impact tasks. Effective queue management is a balancing act between the technical implementation of logic and the constant observation of operational metadata. By systematically assigning priorities at the creation stage and diligently updating the status throughout the item's journey, you provide the necessary telemetry to satisfy both automated and human-led business processes. Remember that the goal of these patterns is to remove the guesswork from operations, ensuring that the system behaves predictably even when the incoming volume is inconsistent. When you integrate these practices, you move from merely building a script to architecting a resilient, observable business service. Your ability to extract these metrics through the control room is what ultimately defines the success of your implementation within an enterprise environment. I will see you in the next lecture. Welcome back. In this session, we will examine the mechanics of handling transactional failures and implementing automated retry logic within Blue Prism work queues. When a process interacts with a work queue, the reality of production environments dictates that not every item will be processed successfully on the first attempt. Orchestrating a robust response to these failures requires a disciplined approach to the mark exception action within the work queue's business object. By invoking this action, you are explicitly communicating the state of a transaction back to the Blue Prism database, which serves as the central ledger for your automation's health. The choice between marking an exception as a system error versus a business error is not merely academic, as it fundamentally dictates whether the queue manager will authorize an automatic retry. System exceptions generally imply an environmental instability, such as an unresponsive web service or a transient network drop, whereas business exceptions represent an invalid data state that no amount of retrying will ever resolve. To implement this effectively, your process must capture the specific failure details and pass them as a string into the exception reason parameter of the mark exception action. This documentation provides the audit trail necessary for operational teams to diagnose why a record failed when it eventually ends up in the exception queue. When an item is marked with a system exception, the Blue Prism runtime environment assesses the retry configuration defined at the queue level in System Manager. If the maximum retry count has not been exceeded, the platform will automatically release the lock on that item and increment the retry counter, making it available for subsequent processing. This mechanism ensures that your automation remains resilient against intermittent failures without requiring human intervention for every minor hiccup in the underlying infrastructure. Isolation is another critical aspect of this design, as we must prevent problematic items from entering an infinite loop that blocks the rest of the queue. By properly configuring the retry count threshold, you effectively create a safety valve that flags poisoned records for manual review after the configured number of attempts. When an item reaches this limit, it is finally moved into a finalized exception status, separating it from the workload remaining for the robots, which allows your process to maintain velocity. This pattern necessitates that your exception handling logic is tightly coupled with your process flow, ensuring that every catch block performs the necessary cleanup and state update. Ignoring these nuances often leads to brittle automations where one corrupt data record brings an entire production cycle to a complete standstill. Consider the workflow where you fetch an item and attempt to map it into your target application, only to find that an expected UI element is missing. In such a scenario, you might catch the exception, differentiate it from a business rule violation, and use the mark exception action to formally log the failure. If the error is indeed transitory, simply allowing the queue management logic to handle the retry is superior to manually building a local loop within your flowchart. This architectural separation enforces a clean boundary between the business logic that executes the task and the infrastructure logic that manages the integrity of the work queue. Over time, this disciplined approach drastically reduces the total cost of ownership for your automation, as it allows your operational staff to filter and resolve only those records that truly require human oversight. See you in the next lecture. Welcome back. Let us discuss how to properly finalize transactional cycles and record performance metrics within Blue Prism work queues. When we reach the conclusion of a transactional processing cycle, the most critical step is managing the state transition of the queue item using the mark completed action. This action does more than simply toggle a status flag. It effectively unlocks the record within the Blue Prism database, allowing other processes or human operators to see that the specific unit of work has been finalized. Failing to execute this step correctly leaves items in an ongoing locked state, which effectively orphans them within the environment until manual intervention intervenes. You must ensure that the transition to a completed state only occurs once the business logic has confirmed that every expected outcome was realized. This practice of state consistency protects the integrity of your audit trails and prevents the accumulation of phantom locks that can degrade overall system performance over time. Beyond basic status management, the platform allows you to record intrinsic transactional metadata directly into the item history through the usage of the output reference fields. By logging key performance indicators such as process duration, extracted data values, or specific reference identifiers, you create an invaluable audit trail that resides permanently alongside the item. This is fundamentally better than relying solely on external log files, as it keeps the context of the automation directly tied to the specific transaction that produced the data. When structuring these analytics logs, you should prioritize consistency in how you format your stored data so that downstream reporting tools can easily parse and aggregate your throughput metrics. If you maintain a disciplined approach to these outputs, you will find that building an executive dashboard revealing the efficiency of your digital workforce becomes a trivial task rather than a grueling data cleaning exercise. Best practices for these closing operations require that you validate the integrity of your data items before finalizing them. A common oversight is to assume that because a process reached an endpoint, the queue item is valid, yet this does not account for partial data processing or incorrect variable mapping. Before triggering the final status transition, perform a brief validation check to ensure that all mandatory fields are populated and that the output references match your architectural expectations. Furthermore, you must consider your organization's database pruning and archiving policies, as the volume of work queue data can grow quite rapidly in high-throughput environments. By keeping your logs concise and relevant, you contribute to a healthy database state that prevents the platform from experiencing unnecessary latency during the retrieval or update of large work queues. Always strive to keep your process logic clean at the end of every loop, ensuring that local variables are reset and orphan threads are properly terminated. If you treat each transaction as a self-contained unit of work that cleans up after itself, you eliminate the risk of environmental contamination where data from one item persists into the next. This level of rigor characterizes a mature developer who understands the long-term implications of maintaining industrial-grade automations. Consistent state management ensures that when something eventually goes wrong, diagnostic efforts are focused on the business logic rather than on investigating locks or corrupted audit histories. By following these patterns, you align your code structure with the expectations of the platform, resulting in more resilient and maintainable solutions. See you in the next lesson. Welcome back. Today, we will discuss how to shift configuration data out of your process logic and into the secure, centralized repository that the Blue Prism environment provides. When we automate business processes, we often encounter values that must change depending on where the code is currently running. If you hard-code a file path or a target system URL directly inside a process, you create a significant maintenance burden. Every time you move your code from a development environment to a testing sandbox or a production server, you would be forced to open the process, modify the data items, and save a new version. This is essentially a violation of the principle of separating concerns, as it couples your business logic with infrastructure-specific details. By leveraging the system manager in Blue Prism, we can isolate these variations into environment variables. These variables act as a contract between the automation and the environment, allowing the process to remain identical across the entire software development lifecycle. By abstracting these values, we ensure that the only thing changing when we promote a release is the configuration stored in the database, not the logic itself. To implement this effectively, we must first establish a rigorous naming convention for our environment variables. Since these variables exist globally across the entire Blue Prism environment, a chaotic naming strategy will quickly lead to confusion and maintenance errors. I prefer a hierarchical scheme that identifies the business unit, the target application, and the specific property, such as Finance, SAP Production URL, or HR Gateway File Path. This structure makes it explicitly clear what the variable does and which system it interacts with, preventing ambiguity during debugging. Once defined in the system manager, these variables allow us to transition from hard-coded strings to dynamic references. Within the process, we simply fetch the value of the environment variable at runtime, which means our logic always receives the value appropriate for the specific server executing the workflow. This approach not only streamlines deployment, but also serves as a security layer, as it allows administrators to restrict, modify permissions. The security of your environment variables is just as important as their accessibility within your workflows. Since these entities are managed within the system manager, they fall under the governance of the Blue Prism security model. You should intentionally limit the ability to create or modify these variables to authorized administrator roles only. By restricting access, you prevent junior developers or unintended processes from overriding critical infrastructure settings, such as database connection strings or server endpoints. When you configure a variable, think carefully about its scope and the sensitivity of the data it contains. While environment variables are excellent for configuration, they should never be treated as a replacement for the credential manager if the data involves sensitive passwords or API authentication keys. Instead, use these variables to store non-sensitive identifiers and operational flags that dictate, for instance, whether a process is running in a verbose debug mode or a reduced log production mode. Managing these variables centrally facilitates seamless migrations between environments without touching your underlying code components. Imagine a scenario where a production server address changes due to a network migration. If your process logic is properly abstracted, you update a single entry in the system manager across all environments. Your processes, which may be running on dozens of digital workers simultaneously, pick up the new value automatically upon the next execution. This decoupling allows your team to focus on building robust, reusable automation logic rather than spending time firefighting environment-specific configuration bugs. It turns your deployments from a manual, error-prone task into a clean, administrative update. You gain a higher level of predictability, and the operational risk associated with deploying new code is significantly reduced. As you continue to build out your maturity in Blue Prism, these patterns will prove essential for scaling your automation ecosystem across the enterprise. I will see you in the next lecture. Welcome back. In this lesson, we explore how session variables offer granular, real-time control over active digital workers. When we design automated processes, we often encounter scenarios where static configurations are insufficient for the fluid nature of production environments. You might be familiar with environment variables, which serve as global constants for your entire infrastructure, yet they lack the volatility required for per-session adjustments. Session variables function differently because they are tied specifically to a running instance of a process within the control room. By defining these in Process Studio, you create an interface for operators or other processes to influence the internal state of a digital worker without needing to restart the session. This level of abstraction allows you to treat your process logic as a dynamic system that responds to external input as it executes. While environment variables provide a reliable foundation for setup, session variables offer the agility needed for tactical operational changes. To implement this functionality, you must first define your variables within the Process Studio environment as session-aware data items. Unlike standard process variables, these session variables appear within the control room interface when you drill down into a running session's properties. By enabling the flag that marks these as session-specific, you expose a hook that permits external modification while the logic is actively traversing your process flow. Consider the scenario where a process is tasked with clearing a massive workload from a queue. You might implement a session variable to represent a threshold for batch size. If the process is moving too slow, a supervisor can manually navigate to the session in the control room and update that threshold on the fly. The process, during its next cycle, reads this updated value and adjusts its behavior accordingly without any downtime. This architectural pattern is particularly valuable when you need to trigger soft stop requests or alter the verbosity of your execution logs. If you find that a robot is consuming excessive resources but you do not want to forcefully terminate the session, you can design a monitoring loop that checks a session variable acting as a flag. When this flag is toggled from false to true in the control room, the robot detects the change and gracefully exits its current loop, commits its work, and finishes the session cleanly. Similarly, you can adjust debug verbosity levels on a per-session basis, which is an invaluable technique for troubleshooting specific issues that only manifest under certain production load conditions. By isolating these controls to the session level, you ensure that your changes do not inadvertently affect other parallel robots running the same process. The distinction between session variables and environment variables ultimately comes down to scope and lifecycle. Environment variables are managed globally through the system manager and remain static across all sessions unless specifically refreshed, making them ideal for database connection strings or directory paths. Session variables are instantiated when the process starts and are destroyed when the session concludes, making them exclusively suited for transient state management. It is easy to confuse the two if you view them simply as data holders, but you must consider the operational context of the data. If the information should change only during a maintenance window, keep it in the environment. If the information must respond to the real-time demands of an operator overseeing the robotic workforce, the session variable is your primary tool for achieving that dynamic control. In mastering this pattern, you move beyond building static automations toward creating truly responsive systems that align with real-world enterprise requirements. You are essentially building a remote control for your robot, turning a black box process into an observable and manageable entity. This is how you bridge the gap between development intentions and the unavoidable complexities of operational control. As you build your processes, think about what knobs and switches you would want at your fingertips if you were the one monitoring the control room. Design those access points early in your development cycle to prepare for the reality of production management. Every piece of metadata you expose via a session variable creates a more resilient and supportable automation solution. I will see you in the next lecture. Welcome back to the course. In this session, we will explore the mechanisms for managing credentials and access control within the Blue Prism environment. In an enterprise environment, hard-coding credentials directly into business objects is a significant security vulnerability. Blue Prism provides the credential manager to address this by offering a centralized, encrypted repository for authentication data. When you create a credential record, you essentially define a name, a username, and a password that is stored securely within the database rather than as a plain text string within your process logic. This approach ensures that sensitive information is never exposed during development, debugging, or execution. The platform handles the underlying encryption, which means that developers interact only with the credential name rather than the secret itself. By abstracting the actual authentication data, we decouple the process logic from the specific environment, which simplifies deployment and significantly enhances security. Configuration of these records involves more than just entering a password. You must consider the expiry tracking feature, which allows administrators to monitor when credentials need to be updated, preventing unexpected process failures due to expired accounts. Granular access control lists are the cornerstone of the least privilege principle here. By default, you should ensure that access to specific credentials is restricted to only those security roles or runtime resources that strictly require them. This prevents unauthorized processes or users from hijacking credentials to gain access to sensitive external applications. When configuring these permissions, think about the specific security groups defined in your environment and map them carefully to the credential records. This rigor ensures that even if a developer has access to the process, they may not necessarily have the right to retrieve the underlying credential data during execution. When it comes to retrieving these credentials in a live process, you must utilize the getCredential action within a business object. This action performs the heavy lifting by securely grabbing the username and password data, injecting them into sensitive data types such as password or specialized secure text items. It is crucial to remember that these data types are designed to mask the contents. If you attempt to view them in the process studio or control room, the platform displays them as a series of asterisks. This prevents accidental exposure in logs, screen recordings, or during active debugging sessions where a developer's eyes might be on the screen. Because the application handles the decryption internally at the moment of use, you maintain a secure chain of custody for your authentication data from the database to the target application. Following the least privilege model, you should also be conscious of the scope associated with these credentials. If a particular business object only requires access to a legacy web application, the permission for that specific credential record should be scoped only to the resources running that specific process. Avoid creating wide-reaching permissions that allow any robot in the environment to grab any credential stored in the vault. This defensive architecture limits the blast radius should any single component of your infrastructure be compromised. Maintaining this degree of separation ensures that your automation remains an asset rather than a liability in the eyes of your organization's security team. Effective credential management is ultimately about minimizing the number of people and components that need to touch the actual secret values. Moving into practical implementation, consider the life cycle of an automated process. When an application changes its password policy, you only need to update the record in the credential manager, and all existing processes will immediately use the new value without needing a code deployment. This agility is a significant benefit of utilizing the centralized vault, as it separates infrastructure maintenance from business logic updates. Ensure your documentation references the credential name, not the username, to keep the process definition clean. By following these patterns, you align your automation development with professional software engineering standards. The goal is always to treat credentials as configuration, which is kept external and protected by layers of access control logic provided by the platform. I will see you in the next lesson. Welcome back to the course. In this lesson, we will explore the architectural patterns required to implement centralized data access in Blue Prism, ensuring your automation remains secure, scalable, and maintainable. When we approach industrial-scale RPA, the naive practice of embedding database connection logic directly inside a process is a recipe for technical debt. Instead, we must treat data access as a distinct, reusable architectural concern that resides within the Object Studio layer, separated from the business logic. By utilizing the OLEDB or ODBC data connection objects provided by Blue Prism, we can establish a consistent interface for executing SQL queries or calling stored procedures. This abstraction allows us to swap underlying infrastructure, such as moving from a development SQL instance to a production environment, by simply updating the configuration parameters rather than rewriting the automation logic. The key is to standardize the way we interact with these utilities, ensuring that every interaction follows a predefined error handling and connection lifecycle pattern. When we encapsulate these calls, we shield the process layer from the messy reality of data access, such as handling driver-specific nuances or connection state management. This approach directly contributes to a more resilient system that acts predictably under varying load conditions. It is not just about moving data. It is about establishing a contract between your automation and the enterprise backend systems. Security, when dealing with enterprise databases or file systems, should never be an afterthought. Hard-coding connection strings is a critical vulnerability that exposes your infrastructure to unnecessary risk, and it complicates lifecycle management across development, test, and production environments. Instead, we should store sensitive parameters, such as database credentials and server endpoints, within the Blue Prism Credential Manager or as environment variables. By injecting these values at runtime, we ensure that credentials are never persisted in the process definition files themselves, adhering to the principle of least privilege. Furthermore, you must implement rigorous data sanitization practices whenever executing dynamic SQL queries to mitigate the risk of injection attacks. Even when utilizing sanitized inputs, one should always enforce timeout boundaries on every database operation. Without explicit timeouts, a hanging query can tie up your runtime resources and eventually consume your entire connection pool, leading to a system-wide bottleneck or process failure. Managing concurrent access is another facet of designing robust data access solutions, particularly when multiple robots access the same underlying database concurrently. You must ensure that your object-level logic accounts for connection pooling constraints and does not exceed the limits set by your database administrators. In scenarios where you are handling external files or web service integrations alongside raw SQL, consider implementing a centralized logging mechanism within your data access object. This allows you to track transactions and debug failures without needing to inspect individual process instances, providing a single source of truth for all data interactions. Furthermore, you must address data leakage by ensuring that data items initialized within an object are properly scoped and cleared after every action. Relying on global state for data storage between database calls can lead to insidious bugs where information from one process execution inadvertently flows into another. By designing your objects to be stateless or properly reset after usage, you guarantee that every data interaction is independent and audit-ready. See you in the next lecture. Welcome back. In this lesson, we will focus on the secure handling of sensitive information through cryptographic and encrypted data types within Blue Prism. When we automate business processes, we are often tasked with handling data that poses significant compliance risks if exposed improperly. Blue Prism provides specific mechanisms to ensure that sensitive fields, such as those containing personal identifiable information or financial records, do not leak into non-secure areas of our infrastructure. One of the primary tools at our disposal is the password data type. Unlike a standard text data type, the password data type is specifically designed to obscure its contents. When a data item is set to this type, the platform ensures that its value is masked within the process logs, the control room monitoring panels, and even during standard debugging sessions in Process Studio. If you reflect on the nature of automation, you realize that visibility is a double-edged sword. While we need to see what a process is doing, we absolutely must prevent sensitive inputs from appearing in clear text where unauthorized users might encounter them. Beyond simple masking, we need to consider how our workflows interact with cryptographic utility functions. Blue Prism allows developers to utilize internal encryption tools to protect data during transit or when stored in persistent collections. If you are reading data from a high-risk transactional input, you should treat that data as volatile and sensitive from the moment of ingestion. By leveraging these cryptographic utilities, we can transform clear text into an encrypted format that remains secure throughout the execution lifecycle. This practice is essential for maintaining adherence to international data privacy regulations such as GDPR or HIPAA, which mandate strict controls over how PII is handled. When you design your objects, consider the lifecycle of the data item. If it does not strictly need to be in clear text for the application's interface, it should remain encrypted or masked at all times. Managing security within an enterprise framework also requires that we pay close attention to data retention boundaries. Just because a robot can process a piece of information does not mean that information should persist in a log file indefinitely. You must configure your workflows to ensure that once a sensitive task is completed, any temporary variables holding sensitive information are cleared or overwritten. If you hold sensitive data in a collection, remember that the collection itself can be inspected in the environment, So proper scoping is vital. Restricting the visibility of data items to only the specific pages or objects that require them minimizes the risk profile of the entire automation solution. These architectural decisions regarding data scoping work in tandem with the encryption tools to create an environment where security is a default property rather than an afterthought. Compliance and corporate policy often dictate the specific strength and type of encryption required for internal systems. As a developer, your responsibility includes ensuring that these policies are mirrored in your configuration of credentials and runtime variables. When we talk about global environment variables or shared resources, we are often dealing with items that need encrypted storage to be accessed securely across different logical environments. By properly utilizing the built-in encryption service, we ensure that even if an underlying database or transport layer is compromised, the sensitive inputs remain unintelligible to external actors. It is about building a defense-in-depth strategy where the data is secure at the field level, the process level, and the environment level simultaneously. See you in the next lecture. Welcome back to the course. In this lesson, we will explore the mechanisms required to manage shared resources and facilitate parallel processing within a Blue Prism environment. When you scale an automation solution across a distributed fleet of digital workers, the primary constraint is rarely the processing power itself, but rather the contention for the underlying target systems. If multiple robots attempt to update a shared file, a centralized database, or a locked network resource at the exact same moment, data corruption or application crashes are inevitable. To build enterprise-grade solutions, you must treat these shared resources as bottlenecks that require explicit coordination. The goal is to move away from serial, single robot execution toward a concurrent model where multiple instances operate in harmony. This requires a shift in how you architect your business objects and process flows, specifically regarding how they request, utilize, and release access to external systems. Implementing effective concurrency controls often requires a combination of architectural patterns rather than a single feature toggle. A common approach is the implementation of a semaphore or token bucket pattern, where a process must acquire a specific asset before performing a write operation on a shared system. In Blue Prism, this can be achieved by utilizing work queues as a pseudo-locking mechanism, where an item serves as a token granting exclusive access to a resource for a defined period. Alternatively, you might leverage the inherent concurrency management provided by the target application itself, such as database-level row locking or file system lock APIs. However, relying purely on the target system can be risky if your automation processes do not gracefully handle locked states, so you must always implement retry logic to navigate temporary contention. Beyond simple locking, you need to consider how to distribute work across runtime resources to minimize the probability of concurrent conflicts. If you have 5 robots attacking the same web interface, you are likely to trigger rate limits or session state conflicts. By utilizing resource pools in the control room, you can segment your automation fleet and bind specific processes to specific pools that interact with distinct instances of your target applications. This spatial separation of work is significantly more robust than attempting to manage locks at the application level. When you design your processes to be idempotent, meaning they can be safely rerun without side effects, you gain the flexibility to handle collisions by simply requeuing the failed item for processing by a different robot at a later time. Balancing workloads across your infrastructure is the final pillar of parallel processing, ensuring that no single robot is overwhelmed while others remain idle. Efficient distribution is managed primarily through the configuration of your work queues, where the prioritization engine acts as the central traffic controller for your automated tasks. By setting intelligent priority levels and using deferred statuses, you can prevent your workers from all grabbing the same high-load tasks simultaneously. This creates a staggered processing cadence that aligns more closely with the capacity of your backend systems. Monitoring the throughput metrics through the system manager will eventually reveal where your bottlenecks exist, allowing you to tune the number of active sessions to match the operational capacity of your environment. See you in the next lecture. Welcome back. We are now moving into the release management section, where we will focus on building robust, deployable packages through the release manager. In this chapter, we will master the mechanics of creating distributable artifacts by examining how to assemble processes, business objects, and their associated dependencies into cohesive release files. We will structure our approach to ensure that nothing is left behind during the migration from development to production. When we approach the creation of a deployable package in Blue Prism, the objective is to encapsulate the entire functional unit of an automation into a standalone B-release file. This file acts as a manifest that tells the target environment exactly which components are required for the solution to execute successfully. We start by selecting the primary process, but the critical work lies in the recursive identification of dependencies. If your process relies on a specific business object, that object must be present in the package, along with every action it exposes. Relying on the target environment to already possess these components is a common source of runtime failures. We must treat the release manager as a holistic tool that bundles everything from work queue definitions to specific credential templates. Environmental dependencies often represent the most fragile aspect of a deployment. We must map variables at the process level to environment-specific values that exist in the target system. If a process expects a file path or a URL stored in an environment variable, failing to package the reference or missing the initialization in the destination environment causes an immediate error. Similarly, when we involve work queues, we are not just moving a process definition, we are potentially defining the work queue structure if it does not already exist. It is good practice to include the queue definition in the initial release to ensure the schema matches exactly what the developer intended. By reviewing the component list before finalizing the manifest, we minimize the delta between our local development setup and the production reality. Version numbering is not merely a bookkeeping exercise. It is a fundamental aspect of lifecycle governance that prevents the deployment of outdated code. We should enforce a consistent semantic versioning scheme that allows us to trace a release back to its specific development iteration. This provides a clear audit trail when debugging issues in a production environment. When we document release notes alongside our package, we are creating a history of changes that informs other administrators about the intent behind the deployment. This metadata becomes invaluable when performing rollbacks or when diagnosing why a specific behavior changed between releases. Integrity validation against target baselines ensures that our package is compatible with the environment's current version of the Blue Prism core installation. A production-ready release file requires a level of diligence that goes beyond simply clicking the export button. We must perform a manual or automated check to ensure that every dependency, security credential, and variable mapping is accounted for before we signal that a package is ready for use. By adhering to these strict packaging standards, we effectively eliminate the risks associated with missing dependencies and incorrect configuration state. We should aim for a zero-omission policy where the act of importing the release is sufficient to restore the entire automation ecosystem on the target tier. This discipline transforms the release manager from a mere utility into a gatekeeper for quality and system stability across our automation landscape. See you in the next lecture. Welcome back. Today, we will examine the technical requirements for promoting automation components across distinct infrastructure environments. We will focus specifically on the mechanics of exporting and importing release packages while maintaining system integrity across your SDLC. When we move a Blue Prism release package from a development environment to testing or production, we are essentially serializing complex objects into an XML format and reconstituting them in a new database. This process is rarely as simple as a direct file transfer because the underlying dependencies, such as environment variables, credentials, and work queues, carry unique identifiers that are bound to the host instance. Before you initiate an export, you must ensure that all processes and objects reflect the finalized versions within the release manager. Attempting to export a package while components are checked out or in a non-production ready state will almost certainly lead to consistency errors during the import phase. It is professional practice to perform a clean compilation of all business objects before packaging them to catch latent issues that compiler checks might otherwise miss. Treat the release file as a snapshot of your current automation logic that must remain immutable once it is generated for delivery to the target environment. Once you have identified the target environment, the import procedure is governed by a wizard that forces you to confront discrepancies between the source and destination metadata. The system will frequently present validation warnings when it detects that essential assets, such as environment-specific variables or credential names, are missing from the target environment. You should interpret these warnings not as minor annoyances to be bypassed, but as critical diagnostic signals indicating a flaw in your deployment preparation. When naming conflicts arise, you are typically presented with choices to overwrite, rename, or ignore the incoming components. Overwriting is common when updating existing processes, but this is a high-stakes operation that can inadvertently wipe out manual patches made directly in production by operational teams. Always verify your permissions within the target environment, as the import process requires elevated rights to modify workflows and update the underlying database records associated with the release. After the import completes, the duty of the developer extends into post-deployment validation, which is often where subtle bugs manifest. You must manually re-verify that every environment-specific variable has been mapped to the correct production values, as these are often stripped or defaulted during an external import. Similarly, check that the credential associations remain valid, ensuring the new processes have the necessary permissions to access application silos or database connection strings. A sanity check involves executing a dry run of the process with restricted data to ensure that the orchestration logic correctly identifies the target application elements in the new infrastructure. If the imported process fails to attach to the application, it is often due to a mismatch between the environment parameters defined in the object modeler and the actual runtime configuration. This phase acts as a final gate, ensuring that the automation behaves identically in production as it did during its lifecycle in the test rig. Despite rigorous testing, anomalies occasionally emerge, necessitating a clear, predefined rollback protocol to minimize production downtime. Ideally, your release strategy should include maintaining a backup of the previous stable version of all components before initiating an import. If a malfunction occurs, having the ability to quickly restore the previous version is not merely a convenience. It is a fundamental requirement for maintaining stable operations. You must document the specific steps required to revert the environment, including clearing out any corrupted queue items or resetting global variables that the failed deployment might have altered. By structuring your deployments to be inherently reversible, you mitigate the risk of catastrophic failure and provide yourself with a safety net that encourages confidence in your release management pipeline. A robust rollback plan is the sign of a mature developer who understands that software in production is dynamic and inherently prone to unexpected environmental interactions. See you in the next lecture. Hello, and welcome to this session on enterprise-level deployment practices. When we transition from individual development to enterprise-scale automation, we must shift our perspective from simply making code run to ensuring that our deployment processes are robust, audit-compliant, and repeatable. The core of this transition involves integrating the Blue Prism Release Manager functionality with broader DevOps orchestration tools that your organization might already utilize, such as Azure DevOps or Jenkins. Relying on manual imports is often a significant point of failure because it lacks the necessary traceability required by ITIL frameworks and compliance auditors. Instead, you need to treat every Blue Prism release file as a version-controlled artifact that sits within your continuous integration pipeline. This means that once a process is tested in a lower environment, the package should be promoted through a series of gates rather than manually moved by a developer. These gates serve as the structural validation checks that prevent broken configurations from ever reaching the production surface. Establishing a clear segregation of duties is not just a suggestion. It is a fundamental requirement for maintaining the integrity of your robotic workforce. In a mature environment, the developer who writes the logic within Process Studio or Object Studio must never be the same person who pushes the button to deploy that code into a production environment. By restricting access rights within the Blue Prism control room and system manager, you enforce a protocol where deployment managers act as the final gatekeepers. These individuals hold the responsibility for reviewing the release manifest, comparing it against the approved change request, and ensuring that all necessary dependencies are met. This separation minimizes the risk of unauthorized changes and provides a clean trail of accountability that is essential when demonstrating compliance to internal governance boards. Automation does not stop at the process level, and that is why you should focus on implementing automated regression testing suites that trigger prior to any deployment approval. Before any code is moved from the test environment to production, Verify that your existing business objects still function against their target applications using an automated validation runner. This is where structural validation checks become invaluable, as they scan the package to ensure that data items, environment variables, and object dependencies are correctly mapped to the target environment settings. By creating these automated quality gates, you force a discipline where failed tests act as an immediate stop-ship signal. Consequently, human intervention is only required if the automated pipeline identifies an anomaly, allowing developers to address potential issues long before they impact actual production operations. Finally, we must integrate our RPA lifecycle with standard ITIL practices, particularly regarding asset inventory and documentation of verification procedures. Every time a build is promoted, the deployment should automatically trigger a log entry in your centralized asset inventory or configuration management database. This inventory must clearly map which versions of processes, objects, and environment variables are currently running on which runtime resources. You should also ensure that deployment verification procedures are documented in a standardized format that is accessible to the production support team. When you align these tasks with ITIL, you provide the support organization with the data they need to troubleshoot incidents effectively. Treating automation with the same rigor as traditional enterprise software ensures that your RPA program remains stable as it matures and scales across the business. I will catch you in the next one. Welcome back. Today, we are stepping into the complexities of dependency management and versioning within the Blue Prism ecosystem. When you build solutions that scale across an enterprise, you are rarely just creating a single process. You are inherently building an ecosystem of interconnected business objects and processes that rely on one another to function correctly. The challenge, of course, is that a change in one fundamental business object can trigger a cascade of failures in every downstream process that consumes it. To maintain a stable automation environment, you must master the art of component tracking and impact analysis. Before you even think about modifying a shared action or altering an underlying database schema, you must utilize the Find References tool. This feature is your primary defense against unexpected regressions because it informs you exactly which objects or processes will be impacted by your changes. Think of it as a form of static analysis that reveals the hidden wiring of your solution before you decide to move a critical component. If you skip this assessment, you risk breaking production workflows simply because you weren't aware that a seemingly minor utility object was being used by 20 different processes across your department. Dependency management is inextricably linked to how we handle the life cycle of our components. Blue Prism provides us with mechanisms like component locking, which is essential when multiple developers are working within the same shared library. By locking a component, you communicate intent to other team members, thereby preventing unauthorized or concurrent modifications that could lead to code corruption or version divergence. However, locking alone is not a substitute for proper discipline and version control. You should cultivate a habit of archiving historic iterations of your objects, effectively saving a baseline before any major refactoring effort begins. This allows you to perform an informed comparison between current states and previous versions, ensuring that if something goes sideways, you have a documented path back to a known good configuration. Without this version history, you are essentially flying blind, forcing you to guess which logic change caused a specific runtime exception or data incompatibility downstream. Managing parallel development tracks requires a high degree of precision, especially when you need to deploy a hotfix without disrupting the ongoing development of new features. When you maintain a branch for production incidents, you must be hyper-aware of your component dependencies so that you don't accidentally pull in unfinished logic from a different development stream. This is where the concept of compatibility becomes critical. You aren't just shipping code. You are shipping a specific version of an object that must interoperate seamlessly with the existing production binaries. If your core object updates require changes that aren't backward compatible, you essentially force a synchronous update across your entire fleet of processes. This is why we modularize our logic to avoid tight coupling between components. When things are loosely coupled, you gain the flexibility to patch one area without demanding a complete revalidation of every single downstream process. Ultimately, your goal is to minimize the friction of deployment while ensuring that the integrity of the total solution remains uncompromised by the evolution of its individual parts. See you in the next lecture. Welcome back. In this session, we will examine the mechanisms required to establish an automated, regulatory-compliant audit trail within your Blue Prism environment. Building a robust audit trail is not merely a logging feature, but a fundamental requirement for enterprise-grade automation that must withstand internal and external scrutiny. When we talk about governance, we are essentially talking about the ability to prove who did what, when they did it, and what data was involved, without compromising the security of that data. Within the Blue Prism ecosystem, the primary control surface for this resides in the System Manager, where administrators define the granularity of logging for specific process runs. By adjusting the logging levels at the session level, you can dictate whether the system captures mere execution milestones or the more verbose output of every stage transition. It is essential to recognize that while verbose logging is invaluable for debugging, it carries a significant performance and storage overhead that should be carefully managed in production environments. You must balance the need for forensic transparency with the practical constraints of database disk space and the potential for inadvertently logging sensitive information. When configuring these logs, you are effectively setting the visibility of your automation's internal state. The properties of each stage in your process provide a checkbox to log information to the session log, but this must be used judiciously. If a stage handles personally identifiable information or restricted credentials, you have an obligation to ensure those values are excluded from the logs. A best practice involves designing your process logic to separate data transformation steps from the final output, ensuring that sensitive values are never passed into a component that is prone to writing to the audit database. You should also consider implementing custom tracking sheets, which act as a secondary, immutable record of transactions. By writing key milestone data into a centralized database table or a dedicated logging object, you create an audit trail that persists independently of the standard agent session logs. Effective auditing goes beyond just recording what happened. It requires the ability to extract and interpret that data when a compliance request arises. Blue Prism provides facilities to export session logs, which can be ingested into external security information and event management systems for long-term retention. During an audit, you might need to filter these logs to show the intervention of specific administrative operators or to trace the path of a specific work queue item through multiple subpages. Forensic debugging, meanwhile, requires a high level of detail, often necessitating temporary increases in log verbosity for specific production processes that are exhibiting unexpected behavior. By maintaining a clean separation between operational data and audit logs, you ensure that the integrity of your compliance record remains untarnished by the noise of routine process execution. Designing these tracking mechanisms requires foresight, as retrofitting logging into an existing, complex process is far more difficult than building it into the initial architecture. Your design should account for the entire life cycle of a transaction, from the initial ingestion in the work queue to the final update of the downstream system of record. Every time an operator manually overrides a process or resets a runtime resource, that intervention should leave a clear, time-stamped footprint in your custom logging store. This level of comprehensive tracking ensures that your automation platform stays compliant with internal security policies and external regulations such as GDPR or HIPAA. By standardizing these patterns across all your business objects and processes, you turn your automation suite into a transparent, audit-ready asset that instills confidence in your stakeholders. We'll see you in the next lecture. Welcome back. Let's discuss the integration of rigorous quality standards into our development lifecycle. This chapter focuses on establishing technical guardrails to ensure our Blue Prism solutions remain maintainable, performant, and secure before they reach production. In professional software development, the difference between a functional process and a resilient enterprise-grade automation often lies in the discipline applied before deployment. We cannot rely solely on the success of a single test run to validate our work. Instead, we must enforce structural integrity through a deliberate code review process. A formal checklist acts as our first line of defense, requiring developers to audit their own work against established naming conventions, which should be consistent across all objects and processes to facilitate easier debugging. When you review a process, start by examining the exception block structure, as improper nesting or missing recovery paths are the most frequent causes of runtime failures. Ensure that every transition is protected by appropriate wait stages with logical timeouts, rather than infinite loops or hard-coded delays, as these are common design smells that mask underlying instability in the application layer. Beyond manual inspection, we must leverage the automated tools available within the Blue Prism ecosystem to maintain consistency. Automated solution scanners are invaluable because they remove human bias and fatigue from the process of detecting common anti-patterns, such as hard-coded variables that should be environment-specific keys or uninitialized data items. These scanners can flag unhandled logical branches where a decision stage leads to an empty path, effectively preventing silent failures that might otherwise go unnoticed during standard functional testing. By shifting these checks into a quality gate that must be passed before a release package is finalized, we institutionalize best practices rather than treating them as optional suggestions. This approach guarantees that resource cleanup requirements, like closing application handles or clearing temporary collections, are satisfied without relying on developer memory alone. Cultivating a peer review culture is not merely about finding bugs. It is an architectural exercise that ensures shared knowledge and longevity of the automation footprint. When another developer reviews your process, they bring a different mental model of the requirements, which often exposes edge cases that you, in your capacity as the author, might have subconsciously ignored. Architects and developers should prioritize consistency in how data is passed between subpages and how business exceptions are distinguished from system exceptions, as this uniformity is what allows team members to jump into projects created by others and provide immediate support. Optimization is a collaborative endeavor, and by scrutinizing the logic flow during these reviews, you can often identify opportunities to refactor complexity into reusable components before it becomes technical debt. This consistent application of quality gates reduces the total cost of ownership for your automation estate, turning disparate robots into a unified, stable workforce. See you in the next lecture. Welcome back. In this lecture, we will explore the practical aspects of manually controlling process sessions within the control room environment. Managing digital workers requires a nuanced understanding of how to bridge the gap between static process definitions and active runtime execution. When you operate within the control room, your primary interface for manual intervention is the resource tree and the session management pane. You typically initiate a process by identifying an available runtime resource, which appears in the list if the Blue Prism Automate agent is running and successfully authenticated against the application server. By manually dragging a published process definition onto an active resource, you effectively create a new session entry. This action prompts the environment to signal the specific runtime resource to initialize its internal engine and begin pulling the process flowchart from the database. It is essential to remember that this process only succeeds if the resource is currently in an idle state. Attempting to drop a process onto a busy resource will often result in a block or a request to queue the execution, depending on your specific configuration. You can also pass startup parameters during this manual initiation phase, which allows for dynamic adjustments to the task at hand without needing to modify the underlying process code. Once a session is active, monitoring is effectively the start of management, but manual intervention is often required when exceptions occur or workload priorities shift. The soft stop command is your preferred mechanism for orderly termination because it signals the process to stop at the next logical opportunity. When you issue a soft stop, the Blue Prism runtime completes the current action or stage and then checks the stop request flag before proceeding to the next logic block. This approach is absolutely critical for maintaining data integrity, especially during complex transactions where partial data commits could lead to state corruption. By choosing a soft stop, you allow the developer to include specific cleanup logic within the process, such as logging the current status, saving unsaved records, or closing application handles properly. It is the professional way to handle a request to cease operations compared to the more volatile alternatives available in the management interface. However, there are scenarios where a process becomes unresponsive or enters an infinite loop, rendering the standard soft stop ineffective. In these emergency situations, you must utilize the hard stop function, which forces the runtime engine to kill the session immediately. This action terminates the process instance without any consideration for the current state of variables or open application windows, often leaving external systems in a locked or inconsistent state. You should strictly reserve this feature for instances where the robot is effectively frozen or behaving in a way that risks infrastructure stability. Once a hard stop is triggered, you must perform a thorough review of the session logs to understand why the process reached a point where it could no longer respond to control signals. Frequently, these situations are the result of unhandled exceptions or poor interaction with external Windows-based applications that have ceased to respond to the runtime's input requests. Managing resource state recovery becomes the subsequent priority after any abnormal termination or interruption of a session. If a runtime resource fails to return to an idle state after a stop command, you may need to manually clear the session from the control room view to release the lock on that specific resource. This involves navigating to the session logs and ensuring that any hanging database connections or session locks are properly accounted for or released by the infrastructure administrator. Furthermore, when dealing with distributed execution, you must verify that the environment variables and session-specific counters are reset before rerunning a process on the same resource. Relying on the system to recover itself is rarely sufficient for production-grade automation. Instead, you must ensure that your manual intervention protocols are documented and consistent. By mastering these manual operations, you guarantee that your digital workforce remains agile and capable of responding to real-world business requirements that fall outside the scope of purely automated schedules. See you in the next lecture. Welcome back. We are now moving into the control room operations sphere to focus on the critical task of diagnosing production failures through session logs. This lesson will provide the technical framework necessary to transform raw logs into actionable intelligence during an incident. When an automation fails in a production environment, the session log within the control room serves as the primary forensic evidence for identifying what went wrong. You should perceive the log not merely as a text output, but as a structured timeline of execution events that mirrors the logic flow designed within Process Studio. The interface allows for targeted filtering, which remains your most potent tool when dealing with complex or long-running processes that generate thousands of log entries per hour. By applying constraints such as specific stage names, timestamps, or particular error types, you can strip away the noise of successful loop iterations to focus exclusively on the point of failure. This systematic refinement is essential because, in a high-volume environment, identifying the exact moment of a technical anomaly is more valuable than reviewing the entire execution history. Always begin by looking for the transition from a standard information log to an exception or warning status, as this usually marks the boundary of the issue. Effective troubleshooting requires that you correlate these Blue Prism session logs with external data sources to build a complete diagnostic picture. If the log indicates a timeout while waiting for a window, you must verify the state of the target application by checking the Windows Event Viewer or the application's own internal audit logs. Relying solely on the Blue Prism exception message is often insufficient, as that message merely reports the symptom rather than the root cause. For instance, if an element is not found, the log will capture the failure of a wait stage, but the actual cause could be a backend server crash or an unexpected modal dialog box preventing the application from reaching the expected state. By aligning the precise millisecond timestamp in the Blue Prism log with the external server logs, you can determine if the infrastructure itself experienced an intermittent network disconnection or a latency spike. This cross-referencing mindset moves you away from guessing at system behaviors and toward empirical observation of the entire software ecosystem. Differentiating between categories of failure is a skill that distinguishes a junior developer from a lead automation engineer. You must train yourself to categorize issues into infrastructure dropouts, application crashes, or input data anomalies based on the signature of the failure within the logs. Infrastructure issues typically manifest as unexpected connectivity errors or lost heartbeats between the digital worker and the Blue Prism server, often occurring during high-load periods. Application crashes are characterized by severe, unhandled exceptions that terminate the interaction process instantly, leaving the object model in an inconsistent state. Conversely, input data anomalies are usually caught by validation stages and manifest as business exceptions, indicating that the logic is functioning as intended, but the provided dataset lies outside the expected business parameters. By maintaining this mental taxonomy, you can interpret the session logs far more rapidly, allowing you to narrow down the problem set and focus your development efforts where they are actually required. When applying these diagnostic practices, ensure you are utilizing the full capabilities of the control room, including the ability to export logs for deep analysis outside of the environment if necessary. While the internal viewer is excellent for real-time monitoring and quick checks, complex issues involving distributed resources often benefit from the ability to compare logs across multiple sessions. Consistency in your logging practices, such as ensuring that your processes contain specific, descriptive entries before sensitive operations, will pay dividends when you are under pressure to resolve a production outage. Think of log entries as the breadcrumbs you leave for your future self, as they need to contain enough context to debug a failure occurring in a different time zone or without direct UI access. By mastering the art of log analysis, you ensure that your deployments remain manageable, auditable, and resilient in the face of inevitable environmental instability. See you in the next lecture. Welcome back. Today, we will explore how to manage resource pools for effective workload distribution. In Blue Prism, a resource pool acts as a logical grouping of multiple runtime resources, designed to behave as a single entity for the purpose of executing automated processes. When you configure a pool, you are essentially creating a collective workforce that can be assigned to process work queues, which is vital for high-volume scenarios. Instead of targeting a specific individual machine, you target the pool name, which abstracts the underlying infrastructure and simplifies session management significantly. This architecture is inherently modular, as it decoupling the process execution from the specific hardware instance. By grouping robots this way, you allow the Blue Prism control room to view a single point of availability rather than managing individual resource states. Understanding this abstraction is fundamental to achieving a resilient automation environment that can handle enterprise-level demands without hard-coding specific resource dependencies. The primary advantage of using resource pools lies in the automatic implementation of dynamic workload balancing. When a process is configured to pull items from a work queue using a resource pool, Blue Prism intelligently distributes the pending transactions across all available active resources within that group. This distribution happens in real time, ensuring that no single machine is overwhelmed while others remain idle, which effectively optimizes your infrastructure utilization rates. If a specific resource experiences a network drop or a hardware-level failure, the workload balancer dynamically reassigns the tasks that were intended for that robot to the remaining healthy members of the pool. This capability provides an automated failover mechanism that maintains continuous processing operations, which is a requirement for mission-critical business automation. Instead of manual intervention, the platform takes responsibility for scaling the active processing capacity based on the current health and connectivity of the pool members. Configuring these pools requires a thoughtful approach to corporate business priority and resource scheduling. You should consider the classification of your tasks and group robots accordingly to prevent resource starvation, where lower priority, high volume processes might monopolize all available capacity. By defining pools based on functional areas or priority levels, you create natural boundaries that ensure your most critical business processes always have access to a predetermined number of resources. Effectively, you are applying a queuing theory to your virtual workforce, ensuring that high-priority items are serviced promptly by resources specifically dedicated to those high-velocity tasks. This separation also aids in operational reporting, as you can monitor the performance of specific pools and understand the throughput capabilities of different segments of your infrastructure. Managing these resources effectively requires that you balance the desire for broad, flexible pools against the need for targeted capacity planning for distinct business requirements. It is also important to recognize that the runtime environment is volatile and machines may transition between states frequently. When you add or remove resources from a pool, Blue Prism updates the available capacity without requiring a restart of the running sessions within the process layer. This fluidity allows developers and administrators to scale the environment up or down based on seasonal demands, such as end-of-quarter reporting, without needing to redeploy or modify the process code itself. The logic for workload distribution is handled internally by the Blue Prism application server, which tracks which items are in progress and which resources are ready to accept new work. By relying on this built-in scheduling logic, you reduce the complexity of the orchestration layer and minimize the chance of errors that arise when attempting to build custom load balancing logic within the processes themselves. Always prioritize the platform's native pooling capabilities to ensure sustained reliability and ease of maintenance in your production environments. See you in the next lecture. Welcome to this chapter regarding the orchestration of automated execution within Blue Prism, where we will examine the mechanics of the schedule management interface. We shall explore how to translate business requirements into temporal execution models to ensure your automations run precisely when needed. Scheduling in Blue Prism is not merely about setting a clock. It is about defining the life cycle of a process execution within the control room. When you enter the schedule management area, you are provided with tools to define recurring tasks that trigger specific processes on designated resources. You begin by creating a schedule, which acts as a container for your execution logic. Inside this container, you define the frequency, which could be hourly, daily, or based on more complex calendar patterns. The platform treats these schedules as automated agents that interact with the runtime resources you have connected to your environment, necessitating a clear understanding of the available infrastructure before you start clicking through the interface. One of the most critical aspects of robust scheduling is the management of exceptions and business interruptions, typically handled through holiday lists and exclusion dates. You can define specific calendar configurations that the scheduler consults before initiating a task. If your business process requires that no automation runs on a public holiday, you do not need to build logic into the process itself. Instead, you maintain a calendar within the system manager that the schedule references during its pre-flight check. This separation of concerns is a hallmark of good architectural design, as it keeps your process studio logic clean and focused solely on business outcomes rather than infrastructure availability. When dealing with high-volume enterprise environments, you will often find that a single business goal requires multiple processes to run in a specific order. You can use the scheduling interface to chain these processes sequentially, ensuring that the second process only triggers once the first has successfully completed. This is achieved by creating task sequences within the schedule. If an upstream process fails, you can configure failure tasks or automated email notifications to alert your support team immediately. This proactive approach to monitoring ensures that you are not left guessing whether a long-running batch process succeeded or stalled in the middle of the night. However, scheduling is not just about linear execution. It is about managing resources to prevent overloading your infrastructure. If you schedule 10 processes to start simultaneously, all of them will attempt to claim available runtime resources, leading to contention and potential session failures. You must balance your peak processing windows by staggering start times or utilizing resource pools, which allow you to group your robots according to their capabilities or service level requirements. Monitoring these schedules requires you to regularly review the execution history to identify bottlenecks or overlapping tasks that consume more bandwidth than your hardware can reliably handle. If a scheduled process unexpectedly locks a resource or enters a hanging state, the scheduling engine provides visibility into the session history, allowing you to troubleshoot the underlying resource contention. By analyzing the duration of these sessions over time, you can optimize your schedule timelines to ensure that tasks that are historically slow do not collide with high-priority processes. Effective schedule management is an iterative process of observation and adjustment, where you fine-tune the timing and resource allocation to match the actual throughput of your environment. This practice turns your control room from a manual control dashboard into an autonomous engine that runs your business operations with minimal human intervention. See you in the next lecture. Hello. Let us look at the operational requirements for maintaining a healthy Blue Prism environment database. As a developer, you might be tempted to assume that database maintenance is strictly an infrastructure or database administration concern. However, in the context of the AD01 certification and real-world Blue Prism deployments, understanding how the control room interacts with the underlying SQL server is critical for maintaining performance. When your production environment grows, the volume of session logs, work queue histories, and internal audit trails expands exponentially. If these tables are left unchecked, the performance of queries within the control room starts to degrade noticeably. This latency does not just affect the user interface. It can introduce bottlenecks when the runtime resources attempt to query the database for the next work item. A well-designed automation solution must therefore consider the life cycle of the data it generates. The primary mechanism for controlling this growth involves the use of the Automate C command line utility. While many developers are comfortable using the Blue Prism client to manage processes, mastering the command line interface is an essential skill for managing your environment's footprint. The archive command allows you to export historical session logs and retired queue data into separate storage files, which effectively keeps your active runtime database lean. You are essentially shifting the data from a high-performance transactional state into a long-term storage format. This is not merely about clearing space. It is about ensuring that the indexes on the core audit tables remain efficient and performant. When SQL query execution plans are bogged down by millions of rows of ancient, irrelevant history, your entire digital workforce experiences the resulting slowdown. When implementing these archiving policies, you must align them with your corporate data retention requirements. Some organizations have strict compliance mandates that demand session history be kept for several years, while others may prefer a rolling 90-day policy. It is vital to determine how much historical performance data is necessary for your long-term business intelligence analytics before you trigger an archive operation. If you architect your archival strategy correctly, you can export necessary telemetry data into external data lakes or reporting warehouses. This allows for long-term trend analysis without forcing the primary control room database to carry the weight of legacy operations. By automating these via command line scripts scheduled in your infrastructure, you ensure that maintenance occurs consistently and without human intervention. Finally, we must address the importance of monitoring the growth trends of your database. As a professional, you should periodically inspect the size of your primary log and queue tables to see if they correlate with your anticipated automation volumes. If you observe that your database is growing faster than expected, it is often a sign that you are logging excessive detail or that your archiving strategy is not keeping pace with production throughput. Consider the impact of the volume of work items you are processing, as every item marked as complete generates database activity. Maintaining this integrity is a core discipline, as it prevents the technical debt that eventually manifests as slow process startups and unresponsive control room dashboards. Treat your database health as a first-class citizen alongside your process logic and exception handling routines. See you in the next lecture.